first few videos, I want to lay the foundation of some core concepts you will need throughout these video tutorials. Let's get started with the basics. So what is a data structure? One definition that I really like is a data structure is a way of organizing data so that it can be used efficiently. And that's all a data structure really is. It is a way of organizing data in some fashion so that later on it can be accessed, queried, or perhaps even updated quickly and easily. So why data structures? Why are they important? Well, they are essential ingredients in creating fast and powerful algorithms. Another good reason might be that they help us manage and organize our data in a very natural way. And this last point is more of my own making, and it's that it makes code cleaner and easier to understand. As a side note, one of the major distinctions that I have noticed from bad, mediocre to excellent programmers is that the ones who really excel are the ones who fundamentally understand how and when to use the appropriate data structure for the task they're trying to finish. Data structures can make the difference between having an okay product and an outstanding one. It's no wonder that every computer science undergraduate student is required to take a course in data structures. It is strange that before we even begin talking about data structures, that we need to talk about the abstraction of data structures. What I'm talking about is the concept of an abstract data type. What is an abstract data type and how does it differ from a data structure? Well, the answer is that an abstract data type is an abstraction of a data structure which provides only the interface to which that data structure must adhere to. The interface does not give any specific details on how a specific data structure should be implemented or in what programming language. One particular example I like to give is to suppose that your abstract data type is for a mode of transportation to get from point A to point B. Well, as we both know, there are many modes of transportation to get from one place to another. So which one do you choose? Some specific modes of transportation might be walking or biking, perhaps even taking a train, and so on. These specific modes of transportation would be analogous to the data structures themselves. We wanted to get from one place to another through some mode of transportation. That was our abstract data type. How did we do that exactly? Well, that is the data structure. Here are some examples of abstract data types on the left and some possible underlying implementation on the right-hand side. As you can see, a list can be implemented in two ways. You can have a dynamic array or a linked list. They both provide ways of adding, removing, and indexing elements in the list. Next, we have a queue and the map, abstract data types, which themselves can be implemented in a variety of ways. Notice that under the implementation for a queue, I put a stack-based queue because, yes, you can have a queue which is implemented using only stacks. This may not be the most efficient way of implementing a queue, but it does work and it is possible. The point here is that the abstract data type only defines how a data structure should behave and what methods it should have, but not the details surrounding how those methods are implemented. Alright, now that we're done with abstract data types, we need to have a quick look at the wild world of computational complexity to understand the performance that our data structures are providing. So as programmers, we often find ourselves asking the same two questions over and over and over again. That is, how much time does this algorithm need to finish? And also, how much space does this algorithm need for my computation? So if your program takes a lifetime of the universe to finish, then it's no good. Similarly, if your program runs in constant time but requires a space equal to the sum of all the bytes of all the files on the internet, your algorithm is also useless. So to standardize a way of talking about how much time and how much space is required for an algorithm to run, theoretical computer scientists have invented big O notation, amongst other things like big theta, big omega, and so on. But we're interested in big O because it tells us about the worst case. Big O notation only cares about the worst case. So if your algorithm sorts numbers, imagine the input is the worst possible arrangement of numbers for your particular sorting algorithm. Or as a concrete example, suppose you have an unordered list of unique numbers, and you're searching for the number 7, or the position where 7 occurs in your list. Then the worst case isn't when 7 is at the beginning or in the middle of the list. It's when 7 is the very last element of the list. For that particular example, the time complexity would be linear with respect to the number of elements and the size of your list, because you have to traverse every single element until you find 7. The same concept applies to space. You could just consider the worst possible amount of space your algorithm is going to need for that particular input. There's also the fact that Big O really only cares about what happens when your input becomes arbitrarily large. We're not interested in what happens when the input is small. For this reason, you'll see that we ignore things like constants and multiplicative factors. So in our Big O notation, you'll often see these coming up again and again and again. So to clarify one thing, when I say n is usually always going to be the input size coming into your algorithm. There's always going to be some limitation of size n. So constant time we refer to as a 1 wrapped around a big O. If your algorithm takes a logarithmic amount of time to finish, we say that's big O of log of n. If it's linear, then we just say n. If it takes like quadratic time or cubic time, then we say that's n raised to that power. If it's exponential, usually this is going to be something like 2 to the n, 3 to the n, any number b greater than 1 to the n, and then we also have n factorial. But we also have things in between these, like square root of n, log of n, n to the 5th, and so on. Actually, almost any mathematical expression containing n can be wrapped around a big O, and is big O notation valid. So now we want to talk about some properties of big O. So to reiterate what we just saw in the last 2 slides, big O only really cares about what happens when input becomes really big. So we're not interested when n is small, only what happens when n goes to infinity. So this is how and why we get the first 2 properties. The first, that we can simply remove constant values added to our big O notation, because if you're adding a constant to infinity, well, that's just infinity. Or if you're multiplying a constant by infinity, yeah, that's still infinity. So we can ignore constants. But of course, this is all theoretical. In the real world, if your constant is of size 2 billion, yeah, probably that's going to have a substantial impact on the running time of your algorithm. However, let us look at a function f, which I've defined over some input size n. If f of n is 7 log of n cubed plus 15n squared plus 2n cubed plus 8, well, big O of f of n is just n cubed, because n cubed is the biggest most dominant term in this function. Alright, now let's look at some concrete examples of how big O is used. So both of the following run in constant time with respect to the input size n, because they don't depend on n at all. So on the left, when we're just adding or doing some mathematical formula, yes, that's constant time. And on the right, okay, we're doing a loop, but the loop itself doesn't depend on n, so it runs also in a constant amount of time. So as our input size gets arbitrarily large, well, that loop is still going to run in the same amount of time, regardless. Now let's look at a linear example. So both the following actually run in linear time with respect to the input size n, because we do a constant amount of work n times. So on the left, we're incrementing the counter I by 1 each time. So f of n is n, and clearly when we wrap this in a big O, we get a big O of n. On the right, a little bit more complicated. We're not incrementing by 1, we're incrementing by 3. So we're going to finish that loop 3 times faster, so f of n is n over 3. So our second example is 2 algorithms that run in quadratic time. So the first one seems obvious. We do n work n times, so n times n is big O of n squared, but observe the second one. I changed the 0 with an I. So pause the video and try to figure out maybe why that's big O of n squared. Okay, let's go over the solution. So first, just focus on the second loop. The first loop isn't as important. So since I goes from 0 to n, the amount of looping done is going to be directly related to what I is. And remember, I is changing from the outer loop. So if we fix I to be 0, we do n work. If we fix I to be 1, we do n minus 1 work. If we fix I to be 2, we do n minus 2 work, and etc. So the question then becomes, what is n plus n minus 1 plus n minus 2 plus n minus 3 and so on? Well, this is a well-known identity, and it turns out to be n times n plus 1 divided by 2. So if we wrap this in a big O, we split our equation, we can see that this is big O of n squared. Now let's look at perhaps a more complicated example. Earlier you may have wondering, how do we ever get these logarithmic or linear rhythmic time complexities? So here's a classic algorithm of doing a binary search, which yields actually a logarithmic time complexity. So what this algorithm does is it starts by making 2 point arrows. One at the very start and one at the very end of the array. Then it selects a midpoint between the two and checks if the value we're looking for was found at the midpoint. And then it has either found it or not. If it has found it, it stops. Otherwise, it discards one half of the array and adjusts either the high or the low pointer. Remark that even in the worst case, we're still discarding half of the array each iteration. So very, very quickly, we're going to run out of array to check. So if you do the math, the worst case is you will do exactly log base 2 of n iterations, meaning that the binary search runs in logarithmic time. A very cool algorithm, a very powerful algorithm. Here's a slightly different example worth going over. So first, notice that there is an outer loop with a counter I that does n work. Then notice that there are 2 inner loops, one that does 3n work and another one that does 2n work. So the rule we use to determine the complexity of this algorithm is to multiply loops on different levels and add those that are on the same, generally speaking. So using the rule above, we can see that it takes n work to do the outer loop, multiplied by 3n plus 2n for both inner loops, which gives us 5n squared, which is big O of n squared. Alright, so this next one looks very similar, but it's actually quite different. So on the outer loop with I, we have I going from 0 to 3n. So there's 3n work done on the outside. But we have to multiply that by what's going on the inside. So on the inside, j goes from 10 to 50. So that does 40 loops, exactly, every loop. So that's a constant 40 amount of work. Plus, however, the second loop. So j is less than n cubed, but j equals j plus 2, so it's accelerated a little. So we're going to finish that loop a little faster. So we're going to get, on the inside, 40 plus n cubed divided by 2, but we have to multiply that by 3n. So if we wrap that in a big O, so big O of f of n, is going to give us big O of n to the fourth, because n to the fourth is the dominant term in our function f of n. There's some other classic examples of big O. So if we have to find all the subsets of a set, that takes an exponential amount of time, because there are 2 to the n subsets. Finding all permutations of a string takes big O of n factorial. Another classic one is merge sort. So if we have n times log n for your merge sort. And if we have to iterate over all the cells of an array of size n by m, we have big O of nm time. Alright, let's talk about arrays. Probably the most used data structure. This is part 1 of 2 in the array videos. The reason the array is used so much is because it forms a fundamental building block for all other data structures. So we end up seeing it everywhere. With arrays and pointers alone, I'm pretty sure we can construct just about any data structure. So an outline for today's video. First, we're going to begin by having a discussion about arrays and answer some fundamental questions such as what, where, and how are arrays used. Next, I will explain the basic structure of an array and the common operations we are able to perform on them. Lastly, we will go over some complexity analysis and look at some source code on how to construct a dynamic array using only static arrays. Discussion and examples. So what is a static array? So a static array is a fixed length container containing n elements which are indexable, usually on the range of 0 inclusive to n minus 1 also inclusive. So a follow-up question is, well, what is meant by being indexable? So answer to this is, this means that each slot or index in the array can be referenced with a number. Furthermore, I would like to add that static arrays are given as contiguous chunks of memory, meaning that your chunk of memory doesn't look like a piece of Swiss cheese with a bunch of holes and gaps. It's contiguous. All the addresses are adjacent in your static array. Okay, so when and where is a static array used? Well, they're used everywhere, absolutely everywhere. It's hard to make a program that doesn't use them, in fact. Here are a few places you may or may not know that do use arrays. So, of course, the first simple example is to temporarily store objects. This is the most common use of arrays that you are probably familiar with. Next is that we use arrays as buffers to store information from an input or an output stream. Suppose you have a really large file, for instance, that you need to process, but that file is so big it doesn't fit in all in memory. So we use a buffer to read small chunks of the file into the buffer or the array one at a time, and so eventually we're able to read the entire file. I also like to use arrays as lookup tables because of their indexing property. So this is a really easy way to retrieve data from a lookup table if you know where everything is and it's supposed to be and at what offset. Next, we can also use arrays as a workaround in a programming language that only allows one return value. So the hack we use then is to return a pointer or a reference to an array, which then contains all the return values that we want. This last example is a bit more advanced, but arrays are heavily used in a programming technique called dynamic programming, with tabulation to cache already computed subproblems. So a classic example of this might be the knapsack problem or the coin change problem. Alright, time to talk about some complexity. So the access time for a static array and a dynamic array is constant because of the property that arrays are indexable. So searching, however, can take up to linear time because we potentially have to traverse all the elements in the array in the worst case, such as if the element you're looking for does not exist. Inserting, appending, and deletion from a static array doesn't really make sense. The static array is a fixed size container. It cannot grow larger or smaller. When inserting with a dynamic array, this operation can cost up to linear time because you potentially have to shift all the elements to the right and recopy all the elements into the new static array. This is assuming we're implementing a dynamic array using static arrays, however. Appending, though, is constant. Doesn't that seem a little strange? Well, when we append elements to a dynamic array, we have to resize the internal static array containing all those elements. But this happens so rarely that appending becomes constant time. Deletions are linear for the same reasons that insertions are linear. You have to shift all the elements over and potentially recopy everything into your static array. Okay, so we have a static array A I've defined at the top. So A contains the values 44, 12, minus 5, 17, 6, 0, 3, 9, 100. Currently all the elements are distinct, but this is not a requirement of an array. Also remark that the very first element, 44, has index or position 0 in the array. Not 1. This confuses many intro computer science students who have no idea. The confusing part is that most, if not all, of mathematics is 1-based, while computer science is 1. Now, if we look at A, you can see that it contains the values 44, 12, minus 5, 17, 6, 0, 3, 9, and 100. Currently, all the elements are distinct. However, this is not at all a requirement of the array. Also remark that the very first element, 44, is indexed or positioned at index of 0 in the array. Not 1, 0. This confuses a lot of intro computer science students. The confusing part is that most, if not all, of mathematics is 1-based, while computer science is 0-based. This is what causes the confusion. But worst of all is quantum computing. I did research one summer in quantum computing during my undergrad, and the field is a mess. It tries to please mathematicians, computer scientists, and physicists all at the same time. And indexing just doesn't work well. Anyways, back to arrays. I should also note that the elements can be iterated over using a for each loop, something that's offered in some programming languages. It doesn't require you to explicitly reference the indices of your array, although the indexing is done internally, behind the scenes. The notation of the square brackets denotes indexing. So array A, square bracket 0, close square bracket is equal to 44, meaning A at position 0 is equal to the value 44. Similarly, A at position 1 is 12, A at 4 is 6, A at 7 is 9, but A at index 9 is out of bounds, and our program will throw an exception. Unless you're in C, it doesn't always throw an exception, unfortunately. Okay, now if we assign position 0 to be -1, that happens. If we assign index 5 to be 18, and if we assign index 6 to be 25. Let's look at operations on dynamic arrays. So dynamic arrays can grow and shrink in size as needed. So the dynamic array can do all similar get, set operations static arrays can do, but unlike the static array, it grows in size dynamically as needed. So if we have A containing 34 and 4, then if we add -7, it gets appended to the end. If we add 34 again, then it'll add it to the end. And we can also remove elements. So you see here our dynamic array shrank in size. Pretty cool, right? Okay, so we already talked about this a little bit, but how do we formally implement a dynamic array? Well, the answer is typically this is done with a static array, but this is not the only way, of course. So first we create a static array with some initial capacity, usually non-zero. So as we add elements to the underlying static array, keeping track of the number of elements added. Once we have to add an element which exceeds the capacity of our internal static array, what we can do is we can double the size, copy all the elements into this new static array, and add the new element we need to add. Let's see an example. So suppose we create a dynamic array with an initial capacity of 2. Then we begin adding elements to it. So the little circle with the slash through it is a placeholder for an empty position. Okay, so we add 7, everything's fine. We add 9, everything's fine. But once we add 3, it doesn't fit in our internal static array, so we double the size of the array, copy all the elements in, and now we can add 3. Now if we add 12, everything's still okay, we're doing good. And if we add 5, okay, we have to do a resize again, so double the size of the container, copy all the old elements into this new larger array, and then finish off by adding 5. And similarly, we can add 6 without any issues. Alright, time to look at the dynamic array source code. This is part 2 of 2 in the array series. So the source code for this video can be found at the following link: github.com/myusername/data-structures. Also make sure you saw the last video so you know what's going on with this array implementation. Alright, here we are in the array class. So I've designed an array class to support generics of type T. So whatever type of data we want to put in this array, that's fine. So here are our 3 instance variables that we care about. R, which is our internal static array. Len, which is the length the user thinks the array is. And capacity is the length of the actual array. Because sometimes our array might have more free slots, and we don't want to tell the user that there's extra free slots that are available. That's just our internal knowledge. So there's 2 constructors. The first one will initialize the array to be of size 16. The other one, you give it a capacity. The capacity, of course, has to be greater than or equal to 0. And then we initialize our array and cast it to a type T. Also notice that I need to put this suppress warnings unchecked just because of annoying generics in Java. So here are 2 simple methods: size, get the size of the array, and check if the array is empty. Pretty self-explanatory. Similarly, for get and set, we just index into the array if we want the value, or set it if we want to set the value. Technically, I should be doing a bounds check for both of these, but I'm not, apparently. Okay, clear. So here we just remove all the data in our array and reset the length. Simple. This next one is the add method, where things actually get a little bit more complicated. So this condition says, hey, if the length plus 1 is greater than or equal to the capacity, then it's time to resize my array. The way I'm resizing is I'm doubling the size of the static array. You don't have to double the size, but I've decided that doubling the size is convenient. So when I double the size, I have to create a new array with the new capacity, copy everything in. This is what this line, or these lines, are doing. It's copying the old values back into this new array, and then it sets the old array to be the new array. And lastly, here we just copy the new value into our array. So this remove as method will remove a particular value at a given index. First, we check if the index is valid. If it's not, throw an index out of bounds exception. Otherwise, grab the data at the remove index, initialize a new array of size length minus 1. Now copy everything into the new array except for when it's at that remove index. Now I'm sure there's easier ways to do this, but I decided to do the following. Maintain 2 indices, I and j. Increment I and j as you go, but when I is equal to the remove index, then we skip over the remove index by fixing j temporarily and using j to lag behind, if you will, while I is still in the original array. So I guess pretty clever overall. And then set the array to be the new array we just generated, reset the capacity, and return the data we have just removed. So this next one, remove, we scan through the array. If we find the object we're looking for, remove it at the index and return true, otherwise return false. Index of is very similar. If you find it, return I, otherwise return -1. Contains just checks if index of is not equal to -1. Alright, this next one, I return an iterator for the array. So an iterator allows us to iterate over the array, providing an abstraction for it. So I need to override 2 methods, and this is hasNext. So there exists a next element in our array if the index is less than the length of the array. I should also be checking for concurrent modification here, just in case someone decides to change the array for some reason while we're modifying it. Might add that later, might not. Also, there's the next method, which just returns the next element in the array relative to the iterator. Okay, and lastly is the toString to get a string representation of this array. Nothing too complicated. Alright, so this is a very simple data structure, it's just a dynamic array. If you look at Java's array list, it looks very, very similar to this. Today we're going to talk about singly and doubly linked lists, one of the most useful data structures out there. This is part 1 of 2. In the second part, we will be looking at some source code on how to implement a doubly linked list. So for today's outline, in the first section, we're going to answer some basic questions concerning singly and doubly linked lists, namely what are they and where are they used. Next, we'll cover some terminology concerning linked lists so everyone knows what I mean when I say the head of the linked list versus the tail of the linked list. Then last in the discussion, we'll talk about the pros and cons of using singly and doubly linked lists. Then how to insert and remove elements from both singly and doubly linked lists, as well as some source code. So stay tuned. Alright, discussion. So what is a linked list? Linked list is a sequential list of nodes that hold data which point to other nodes also containing data. So below is an example of a singly linked list containing some arbitrary data. Notice that every node has a pointer to the next node. Also notice that the last node points to null, meaning that there are no more nodes at this point. The last node always has a null reference to the next node. For simplicity, I will omit this in the following slides. Okay, so where are linked lists used? One of the places they get used the most is actually in the abstract data type implementation of lists, stacks, and queues because of their great time complexity for adding and removing elements. You also see linked lists in things like circular lists, making the pointer of the last node point to the first node. So circular linked lists are used to model repeating event cycles, maybe like having a round-robin ordering on a bunch of elements or representing corners of a polygon. So definitely a lot of uses there. Linked lists can also be used to model real-world objects, such as a line of train carts. That could be useful. And moving on to some more advanced examples, we also heavily use linked lists in hash table separate chaining and for adjacency lists and graphs. We'll get to those in a later video. Okay, a bit of terminology surrounding linked lists. First thing you need to know when creating a linked list is that we always maintain a reference to the head of the linked list. This is because we need somewhere to start when traversing our list. We give a name to the last element of the linked list also. This is called the tail of the list. Then there are also the nodes themselves, which contain pointers. Pointers are also sometimes called references, and these pointers always point to the next node. You should also know that the nodes themselves are usually represented as structs or classes when actually implemented. We'll get to this when we look at the source code. Okay, singly versus doubly linked lists. So concerning the kinds of linked lists that there are two types, singly linked and doubly linked. Singly linked lists only contain a pointer to the next node, while doubly linked lists not only contain a pointer to the next node, but also to the previous node, which makes it quite useful sometimes. This is not to say we cannot have triply or quadruply linked lists, I just wouldn't know where to place the additional pointers. Pros and cons of doubly linked lists. So there are trade-offs between picking a singly and a doubly linked list. What are they? If we look at the singly linked list, we observe that it uses less memory. Why? Well, pointers to nodes can actually take up a lot of memory. If you're running on a 64-bit machine, references use 8 bytes. On a 32-bit machine, 4 bytes each. So having a singly linked list means you only need one pointer for each node, hence twice as much memory is saved. A downside, however, is that you cannot access previous elements because you don't have access to them. You would need to traverse from the head of the linked list all the way up to the previous node to find it. Now concerning doubly linked lists, well, a great pro is that having access to the tail, we can easily traverse the list backwards, something we can't do with a singly linked list. Also, having a reference to a node you want to remove, you can remove it in constant time and patch the hole you just created, because you have, again, access to both the previous and the next nodes. This is something you cannot do with a singly linked list. You would leave the list severed in two. A downside, however, to the doubly linked list is it does use up twice as much memory. Okay, let's go into some implementation details on how we can create linked lists and remove elements from linked lists. Starting with singly linked lists. So here is a singly linked list. I've outlined where the head and the tail is. Now we want to insert 11 at the third position, where 7 is currently. Let's walk through an example. So the first thing we do is we create a new pointer, which points to the head. This is almost always the first step in all linked list operations. Now what we're going to do is seek up to, but not including, the node we want to remove. So if we seek ahead, we advance our traversor pointer, setting it equal to 5's next node, which is now 23. And now we're actually already where we need to be to insert the next node. So we create the next node, that's the green node, 11. And we make 11's next pointer point to 7. And the next step is to change 23's next pointer to be 11. Remember, we have access to 23's next pointer because we have a reference to it with the traverser. Okay, and now if we flatten out the list, we can see that we've correctly inserted 11 at the right position. And we're done. Okay, alright, time to insert with a doubly linked list. This is much trickier because of all the pointers flying around, but it's the exact same concept. Notice that the doubly linked list not only has pointers to the next node, but also to the previous node. We also have to change those in the insertion phase. Okay, create a traverser pointer which points to where the head is and advance it until you are just before the insertion position. So we advance the traverser by 1, and now we're just before the node, so we stop traversing. Let's create the new node, which is node 11. Point 11's next pointer to equal 7. Also point 11's previous pointer to be 23, which we have a handle on because of the traverser. Now we make 7's previous pointer equal to 11, so we can go backwards from 7 to 11. And the last step, make 23's next pointer equal to 11. This is so that we can go forwards from 23 to 11. So in total, remark that we changed exactly 4 pointers. So if we flatten out the list, you can see that 11 has been inserted in the correct position. Alright, now how to remove elements from a singly linked list. So suppose we want to remove the node with a value 9. How do we do this? Well, the trick we're going to use is not to use one pointer, but 2. You can use one, but for visual effects it's easier to show you how it is done by using 2. So we create pointers trav1 and trav2 for traverser 1 and traverser 2 respectively. So traverser 1 points to the head. Traverser 2 points to the head's next node. Now what we're going to do is advance trav2 until we find the node we want to remove, while also advancing trav1. Okay, we have found node 9, so this is the stopping point. I'm going to create another pointer, to the node we wish to remove, so we can deallocate its memory later. Okay, so now I had to have advanced trav2 to the next node. And node 9 has turned red. I've done this to indicate that at this point, node 9 is ready to be removed. I'm just keeping it around for the visual effect. Okay, so now set trav1's next pointer to be equal to trav2. And now it is an appropriate time to remove the temporary pointer because we're doing nothing with it. And their temp has been deallocated. Make sure you always clean up your memory to avoid memory leaks. This is especially important in C and C++ and other programming languages where you manage your memory. Now you can see that 9 is gone and our singly linked list is shorter. Okay, now for the last bit of implementation, let's look at how to remove nodes from a doubly linked list, which is actually easier in my opinion to removing from singly linked lists. The idea is the same. We seek up to the node we wish to remove, but this time we only need one pointer. One traverser pointer, because each node in the singly linked list has a reference to the last node, so we don't need to manually maintain it like we did with the singly linked list. So let's start trav at the very beginning and seek until we hit 9. Okay, we've reached 9, and we want to remove it from the list. To do this, set 4's pointer to be equal to 15. We have access to 4 and 15 because they are trav's previous and next pointer, respectively. Similarly, set 15's previous pointer to equal 4. Notice that trav is now red, meaning it is ready to be removed. So we get rid of trav, and now if we flatten out the doubly linked list, we see that it no longer contains 9. Let's do a bit of complexity analysis on linked lists. How good actually are linked lists? On the left column, we have singly linked lists, and on the right, doubly linked lists. The complexity for searching in a linked list is linear, in the worst case, because if the element we're looking for is not there, we have to traverse all of the n elements. Inserting at the head, though, is constant time, because we always maintain a pointer to the head for a linked list, and hence we can add it in constant time. Similarly for the tail. To remove the head of a singly linked list and a doubly linked list is also constant time. Again, because we have a reference to it, so we can just remove it and advance the head by 1. However, removing from the tail is another story. It takes linear time to remove elements from a singly linked list. Can you think of why? Well, even if we do have a reference to the tail in a singly linked list, we can remove it, but only once, because we can't reset the value of what the tail is. So we have to seek to the end of the list and find out what the new tail is equal to. Doubly linked lists, however, do not have this problem, since they have a pointer to the previous node, so we can continually remove nodes from the tail. And finally, removing somewhere in the middle is also linear time, because in the worst case, we would need to seek through n-1 elements, which is linear. Alright, time to look at some doubly linked list source code. This is part 2 of 2 in the linked list series. So the link for the source code can be found on GitHub at github.com/WilliamFiset/data-structures. Please star this repository if you find the source code helpful so that others may also find it. And also make sure you watch the first part of the linked list series before continuing. here we are in the source code. We're looking at the implementation of a doubly linked list in Java. So first, notice that I have declared a few instance variables. So we are keeping track of the size of the linked list, as well as what the head and the tail currently are. To begin with, the head and the tail are null, meaning linked list is empty. Furthermore, we will be using this internal node class quite excessively because it contains the data for our nodes, and it also contains previous and next pointers for each node, since this is a doubly linked list. So we have one constructor for the node, namely the data and the previous and the next pointers themselves. We need both, otherwise we can't do much. So this first method I have declared here is to clear the list. It does so in linear time by going through all the elements and deallocating them one at a time. It deallocates them by setting them equal to null. So we start a traverser at the head, we loop while the traverser is not equal to null, meaning there are still elements in the list, and then we do our deallocation business. And at the end, we set the size equal to 0 and reset the head and the tail. Perfect. These size and empty methods are pretty self-explanatory. Get the size and check if the size of our linked list is empty. Okay, so here I have a public method to add an element. By default, we're going to append to the end of the linked list or at the tail. But I also support adding to the beginning of the linked list. So how we do this, if this is the first element, aka the list is empty, then we set the head and the tail to be equal to the new node, which has, as you can see here, both previous and next pointers set to null. Otherwise, if the list is not empty, then we say the head's previous pointer is equal to this new node. And then we set the head pointer to be whatever head's previous is. So we back up the pointer in a sense, and we also don't forget to increment the size. A very similar thing is done when we want to add to the tail of the linked list, except we're moving the tail pointer around. Okay, let's move to peek. So peeking is just looking at either the element at the beginning of the linked list or at the end of the linked list. And we throw a runtime exception if the list is empty, because it doesn't make sense to peek an empty list. Okay, now we get to the first more complex method, which is remove first. So this is if we want to remove the head of the linked list. So we can't do much if the list is empty. Otherwise, we get the data, we extract the data at the head, and then move the head pointer forward. We decrease the size by 1. So if the list is empty, we set the tail to be null as well. So both the head and the tail are now null. Otherwise, we deallocate the memory of the previous node that we just removed. This is especially important if you're in C or C++. Make sure to free or delete your pointers. Then at the end, we return the data. A very similar thing is done for last, except we're using the tail this time to remove from the tail of the linked list and not the head. Okay, and here's a generic method to remove an arbitrary node. Remark that I set this to private because the node class itself is private, so the user shouldn't have access to the node. That's just something we're using internally inside the linked list data structure to manage the list. So if the node that we're removing is either at the head or the tail, detect that and call our methods either remove first or remove last. Otherwise, we know we're somewhere in the middle of the linked list. And if we are, we make the pointers adjacent to our current node equal to each other. So we're effectively skipping over the current node. And then, of course, don't forget to clean up your memory and return the data. So we have to temporarily store the data, of course, before we delete the node. Otherwise, we've deleted the node and the data is already gone. Now, suppose we want to remove a node at a particular index in our linked list. Yes, we can do this. Even though our nodes are not explicitly indexed, we can pretend that they are. So first check that the index is valid. Otherwise, throw in a legal argument exception. So here we are trying to be a bit smarter than just naively going through the linked list. Either we're going to start searching from the front of the linked list to find our index, or from the back, depending on if the index is closer to the front or to the back, although this method remains linear. So for the remove method, we want to be able to remove an arbitrary value from our linked list, which is object. So we're going to also support searching for null values in case someone decided that the value of the node should be null. That's fine. So we check that special case. Otherwise, we traverse through the linked list until we find a null element and then remove that node and return true. We return true if we've actually found the element we want to remove. Otherwise, we return false down here. In this else statement, we search for the element we want to remove. We use the dot equals method to check if we found the element. If so, remove that node and return true. Okay, here we have a related method, which is index of. So this is not remove at an index or remove a value, but get whatever index this object is at. Again, support searching for null, so even if our value is null, we'll just return the first place we find a null element. So again, traverse the linked list. Otherwise, search for a non-null element, and also increment the index as we go. We can use the index of for our method contains to check if an element is contained within a linked list, because we return -1 if the element is not found. Something that's useful sometimes is to have an iterator for a linked list. This is also trivial to implement. Just start a pointer, traverse at the head, and traverse until you reach the end. Notice I'm not checking for concurrent modification error, but if you want to, it's pretty easy to do that. And lastly, at the very bottom, we have the toString method to print a string, or to get rather a string representation of our linked list. May I begin by saying that the stack is a remarkable, absolutely remarkable data structure. One of my favorites, in fact. This is part 1 of 3 in the stack videos. Part 2 will consist of looking at a stack implementation, and part 3 will be some source code for how a stack is implemented using a linked list. So here are the topics that we'll be covering in this video, as well as the others. First, we will answer the question about what is a stack and where is it used. Then we will see some really cool examples of how to solve problems using stacks. Afterwards, we will briefly look at how stacks are implemented internally and the time complexity associated with the stack's operation. And lastly, of course, some source code. Moving on to the discussion about stacks. So what is a stack? A stack is a one-ended linear data structure which models a real-world stack by having 2 primary operations, namely push and pop. Below you can see an image of a stack I have constructed. there is one data member getting popped off the top of the stack and another data member getting added to the stack. Notice that there is a top pointer pointing to the block at the top of the stack. This is because elements in a stack always get removed and added to the top of the pile. This behavior is commonly known as LIFO, or last in, first out. Let's look at a more detailed example on how a stack works and how things are added and removed from a stack. So let's walk through an example. On the left side, I have some instructions on what we need to add and remove to the stack. So the first operation is a pop. So we remove the top element from the stack, which is apple. So boom, apple is gone. Now we push onion onto the stack. So we add onion to the top of the stack. Next instruction says to push celery onto the stack. Next is watermelon, which we put on top of the stack. Next operation says to pop, so we remove the element at the top of the stack. This is the watermelon we just added. The next operation, also a pop, so we remove from the top of the stack. This is celery. And the last operation, push lettuce onto the stack. So we add lettuce on the very top of the stack. So as you can see, everything operates on the top of the stack. We don't have access to anything else but the top of the stack. This is critical in our understanding of how a stack works. So when and where is a stack used? Stacks are surprisingly used absolutely everywhere. They're used in text editors to undo text you've written, in browsers to navigate backwards and forwards. They're used in compilers to make sure you have the correct number of matching braces and in the right order. Stacks are used to model real-world stacks such as books, plates, and even games like the Tower of Hanoi, which we'll get to shortly. Stacks are also used behind the scenes to support recursion by keeping track of previous function calls. When a function returns, it pops the current stack frame off the stack and rewinds to the next function that is on the stack. It's rather remarkable that we use stacks all the time in programming and never even notice it. Something else you can use stacks for is to perform a depth-first search on a graph. A depth-first search can be done manually by maintaining your own stack or by using recursion. Well, guess what? Both use stacks, as we have just discussed. Complexity analysis. So the following complexity table assumes that you implemented a stack using a linked list. Pushing takes constant time because we have a reference to the top of the stack at all times, while the same argument goes for popping and peeking. Searching, however, still takes linear time. The element we're searching for isn't necessarily at the top of the stack, so we may need to scan all the elements in the stack, hence requiring linear amount of work. Now here's a cool example of a problem using stacks. Problem. So given a string made up of the following brackets, round brackets, square brackets, curly brackets, determine whether the brackets properly match. So analyze the examples below to understand what type of bracket sequence is valid and which ones are invalid. So before I show you the solution, try and come up with a solution yourself. Hint, use a stack. Okay, in this first example, consider the following bracket sequence. As we are processing the string from left to right, I will be displaying the current bracket and the associated reversed bracket. So let's begin. For every left bracket we encounter, we simply push those on the stack. So this is a left square bracket that I've highlighted in light blue. So we push this one on the stack. Same goes for the next left square bracket and for this left curly bracket. Okay, this is a right square bracket. So we encountered a right square bracket. So we need to do two checks. First, we check if the stack is empty. If so, the bracket sequence is invalid. But if there are still things in the stack, then we pop the top element and check if its value is equal to the reversed current bracket. Right now, the top element is equal to the reversed bracket, so we are good. Next is a right square bracket again. So is the stack empty? No, it isn't, so we're good. Is the top element of the stack equal to the reversed bracket? Yes, it is, so let's keep going. A round left bracket. Let's push it onto the stack. A right bracket. Is the stack empty? No? Okay, so we're good. Is the top element of the stack equal to the reversed bracket? Yes, okay, so we're good. Another right bracket. Is the stack empty? No, okay, good. And is the top element of the stack equal to the reverse bracket? Yes, okay, good. And now we're done processing the string. We need to make sure the stack is empty now. Why is that? Well, in case the last few characters in the bracket sequence were left brackets, they would still be in the stack, right? But our stack is empty, so we can conclude that this bracket sequence is indeed valid. Alright, let's do another example with another bracket sequence. So try and work this one out. So the first bracket is a left bracket, so we push on to the stack. The second bracket is also a left bracket, so we push on to the stack. This next bracket is a right bracket, so let's check if the stack is empty. No, it's good. And is the top element of the stack equal to the reverse bracket? Yes, it is. This next bracket is a right bracket. Is the stack empty? No, so we're good. And is the reverse bracket equal to the bracket at the top of the stack? No, it isn't. So this bracket sequence is invalid. So here's the pseudocode of the algorithm we just ran through. So if we let S be a stack, then for every bracket in our bracket string, we can get the reversed bracket for that current bracket easily. So if our bracket is a left bracket, push it onto the stack. Otherwise, we check if the stack is empty and if the element at the top of the stack is not equal to the reversed. If either of those conditions are true, then we return false. Otherwise, we return whether the stack is empty or not. And if it is empty, then we have a valid bracket sequence. Otherwise, we do not. I want to take a moment and look at the Tower of Hanoi, a very popular game amongst mathematicians and computer scientists, to see how it relates with stacks. The game is played as follows. You start with a pile of disks on the first peg on the left, and the objective of the game is to move all the disks to the rightmost disk pile. At each move, you can move the top disk of any pile to any other pile with a restriction that no disk be placed on top of a smaller disk. So we can think of each peg as a stack, because we're always moving the top element in a peg and placing it on another peg. So shall we play? I will let the animation run and you will see how each peg acts like a stack. It's pretty cool. So you just saw how transferring elements from one peg to another is exactly the same as popping a disk from one stack and pushing that same disk onto another stack, given that the disk you're placing on top is smaller. So that's really cool. Welcome to part 2 of 3 in the stack series. This is going to be a short video on one way to implement a stack. So those stacks are often implemented as either arrays, singly linked lists, or even sometimes doubly linked lists. Here I will cover how to push nodes onto a stack with a singly linked list. Later on, we will look at the source code, which is actually written using a doubly linked list. Okay, to begin with, we need somewhere to start to begin our linked list. So we're going to point the head to a null node. This means that the stack is initially empty. Then the trick to creating a stack using a singly linked list is to insert the new elements before the head and not at the tail of the list. This way, we have pointers pointing in the correct direction when we need to pop elements off of the stack. As we will soon see, the next element, however, we need to push onto the stack is at 2, so let's do that. So we create a new node, adjust the head pointer to be the newest node, and then hook on the node's next pointer to where the head was before. And we use the same idea for 5 and also 13. Now let's have a look at popping elements. This isn't too hard either. Just move the head pointer to the next node and deallocate the last node. So here we pop the first node off the stack and set the node's reference to be null, so that it will be picked up by the garbage collector if you're coding in Java, and it will since there are no other references pointing to it. If you're in another programming language that requires you to explicitly deallocate free memory yourself, like C or C++, now is the time to do that, or you will get memory leaks. Getting a memory leak in a data structure is one of the worst kinds of memory leaks, especially if it's a custom data structure that you intend on reusing. So keep watching out for that, not only in this video, but in all the data structures that we will be covering. If you see in an implementation that I'm not correctly cleaning up my memory, please point it out to me, or send a pull request to the GitHub repository so we can patch that. Okay, so we keep proceeding by removing the head and advancing the head pointer down to the next node. Pop again, and pop again. And there we go, we've stopped popping, we've reached the last node, and the stack is now empty. Welcome to part 3 of 3 in the Stack series videos. Today we'll be looking at some source code for a very simple stack. So the source code can be found at github.com/WilliamFiset/data-structures. Make sure you understood part 1 and 2 of the stack series before continuing, so you actually know how we implement a stack using a linked list. Also, if you like this video series and the implementation of the stack data structure I'm about to present to you, then please start this repository on GitHub so that others can have an easier time finding it as well. Here we are in the stack source code. This is an implementation in the Java programming language. So the first thing you may notice is here I have an instance variable of a linked list. This is the linked list provided by Java. In fact, it's a doubly linked list provided by Java. This is the linked list they provide in their package java.util that I will be using today instead of the one that I created in the linked list videos. This is just for portability in case you want to use the stack for whatever reason. So we have two constructors. We can create an empty stack, or we can create a stack with one initial element. This is occasionally useful. This first method, we can get the size of the stack. So to do that, we return the size of the internal linked list with all the elements of our stack. Easy. We can also check if the stack is empty by checking if the size is 0. So this next one is just push. So to push an element onto the stack, we just append that element as the last element in our internal linked list. Easy enough. We can also pop an element off the stack. So to do this, we check if the stack is empty. If it is, then we throw an empty stack exception because we can't pop an element off of an empty stack. That doesn't make sense. Similarly, the same thing with peek. We can't observe what the top element of the stack is if the stack is empty. And if it's not, then we can peek the last element of our list. And lastly, we can return an iterator to allow the user to iterate through our stack. This iterator returns an iterator for our linked list, which supports concurrent modification errors. So this was a really quick implementation of a stack. It's only like 50 lines of code. Let's talk about queues, probably one of the most useful data structures in computer science. So this is going to be part 1 of 3 in the queue series. So the outline of things we'll be looking at. First, we're going to begin by talking about queues and what they are. Then we're going to go into some complexity analysis concerning queues. Then we'll discuss the implementation details of enqueuing and dequeuing elements from a queue, followed by some source code at the very end in the last video. So a discussion about queues. So what exactly is a queue? So below you can see an image of a queue, but a queue is just a linear data structure that models a real-world queue, having 2 primary operations we can do, which are enqueuing and dequeuing. So every queue has a front and a back end. We insert elements through the back and remove through the front. Adding elements to the back of the queue is called enqueuing, and removing elements from the front of the queue is called dequeuing. However, there's a bit of terminology surrounding queues because there's not really any consistency. When we refer to enqueuing and dequeuing, many people will use multiple different terms. So enqueuing is also called adding, but also offering. A similar type of thing happens when we're talking about dequeuing. So this is when we remove things from the front of the queue. This is also called polling elements. However, some people will also refer to this as removing an element from the queue. But the problem with saying that is that can cause some ambiguity. Did they mean removing from the front of the queue specifically, or from the entire queue? Make note that if I say removing, I'm going to be referring to removing from the front of the queue unless I say otherwise. So let's look at an example of how a queue works in some detail. However, first notice that I have labeled the queue's front and back ends so you know where I'm going to be enqueuing and dequeuing from respectively to avoid confusion. First instruction says to enqueue 12, so we add 12 to the end of the queue. Then dequeue, so we remove the first element from the front of the queue, which is 55. Another dequeue operation, this time we remove -1 from the front of the queue. Next, enqueue 7, so add 7 to the back of the queue. Dequeue, so remove the front element, being 33. And lastly, enqueue -6, so add it to the back of the queue, just like that. So now that we know what a queue is, where does this data structure actually get used? Well, a classic example of where a queue gets used is to model a real-world queue where you're waiting in a line at a movie theater or in a line at a restaurant. For instance, have you ever been to, say, McDonald's, where all the caches are full, and as soon as one of them gets free, the next person in line gets to order food? Well, that's a queue. So queues can also be really useful if you have a sequence of elements coming in, but you only need to keep track of, say, the X most recent elements. Well, you can add those elements to your queue, and once your queue gets larger than X elements, just dequeue, essentially. Queues are also often used in server management. So suppose for a moment that you have a web server that's idly waiting for requests from people to use your website, that at any given moment you can simultaneously serve up to 5 people, but no more. If 12 requests come in a short amount of time, you're not going to be able to process all of them as new ones come in. So what you do is you process the 5 that you're able to, and the remaining 7 get to chill in a queue, waiting to be served. And whenever you finish processing a request, you dequeue in the next request, and then you start processing it, and you do this until the queue is empty. While you're doing this, if more requests come in to access your web page, well, you just add them to the end of the queue. Queues are also used in graph theory to perform a breadth-first search traversal on a graph, which is actually really useful. We're going to see this example in the next video. Alright, now concerning complexity analysis of a queue. So as we've seen, it's pretty obvious that enqueuing and dequeuing operations are constant time. There's also another operation on a queue I have not mentioned yet, and this is peaking. Peaking means that we're looking at the value at the front of the queue without removing it. This is also constant time. However, checking if an element is contained within the queue is linear time, since we would potentially need to scan through all of the elements. There's also element removal, not in the sense of dequeuing or polling, but in actually removing an element from the queue internally. This also requires linear time, since we would have to scan through all elements in the worst case. In this video, we're going to have a look at how queues are used to do a breadth-first search, and then we're going to look at the actual implementation details of how enqueuing and dequeuing elements works. Okay, on to the breadth-first search example. So a breadth-first search is an operation we can do on a graph to do a graph traversal. If you don't know what I mean when I say graph, I mean a network, not a bar graph or a line graph or anything like that. But first I should explain the breadth-first search. In the breadth-first search, the objective is to start at a node and traverse the entire graph. First by visiting all the neighbors of the starting node, and then visiting all the neighbors of the first node you visited, and then all the neighbors of the second node you visited, and so on and so forth, expanding to all the neighbors as you go. So you can think of each iteration of the breadth-first search as expanding the frontier from one node outwards at each iteration as you go on. So let's begin our breadth-first search at node 0. So I'm going to label node 0 as yellow and put it in the frontier, or the visiting group. And now I'm going to visit all the neighbors of 0, being 1 and 9, and add those to the frontier. And then I'm going to visit all the neighbors of 1 and 9, being only 8. Similarly for 8, so 7, then visit all the neighbors of 7. So I added a bunch of elements to my frontier. And now visit all the neighbors of the yellow nodes. And now we're done our breadth-first search because we no longer have any elements on the frontier. Notice that there's 12 that is still unvisited because 12 is a loner node on an island all by itself, so we're not able to reach it via breadth-first search, which is fine. So suppose we wanted to actually code a breadth-first search. How would that be done? Well, the idea is to use a queue. So first, we add the starting node to our queue, and then we mark the starting node as visited, and while our queue is not empty, we pull an element from our queue, or dequeuing, and then for every neighbor of this node we just dequeued, if the neighbor has not been visited yet, mark the neighbor as visited and add it to the queue. So now we have a way of processing all the nodes in our graph in a breadth first search order. Really, really useful. A very, very popular graph traversal algorithm. So now let's look at implementation of queues. So let's begin with enqueuing. So it turns out that you can implement the queue abstract data type in multiple different ways. But the most popular methods are to either use arrays, singly linked lists, or doubly linked lists. If you're using an array, you have to make sure your array is going to be big enough if it's a static array. If it's a dynamic array, then you'll be fine. But here I'm going to show you how to do it with a singly linked list, but in the source code we're using a doubly linked list, so stay tuned for that. In a singly linked list, we're going to have a head pointer and a tail pointer. So initially they're both null. But as we enqueue, we just add the first node, so nothing really interesting is going on right now. But as we enqueue more elements, you can see that we're pushing the tail pointer forward. So we're adding a node and then getting the tail pointer to point to the next node. Now dequeuing is a bit of the opposite. Instead of pushing the tail forward, we're going to be pushing the head forward. So push the head forward one, and then the element that was left over was the one we wanted to dequeue and return to the user. So when we push the head pointer forward, we set the last node to null so that it can be picked up by the garbage collector if you're in Java. If you're in another programming language which requires you to explicitly deallocate or free memory yourself, like C or C++, now's the time to do that. So you see, as we keep dequeuing, we're just pushing the head forward and forward again. And at the very end, if we add a bunch of elements and then remove them all, then the head and the tail again point to null, which is where we started. Alright, now it's time to have a look at some source code for a queue. So I implemented a queue, and you can find the source code at the following link on github.com/myusername/data-structures. Also make sure you have watched and understood parts 1 and 2 from the queue series before continuing. Alright, here we are looking at some source code for a queue. So this source code is in the Java programming language, although you can probably translate it into any programming language that you need. So the first thing to remark is I have an instance variable here of a linked list. So this is Java's implementation of a doubly linked list. We also use this in the stack implementation. As you'll see, the queue and the stack implementations are very, very similar. So here I have two constructors, one that'll create just an empty queue and another optional one which will create a queue but with a first element. In fact, I should probably check if this is null, but we might want to allow null elements, so let's just leave it like that. So the next method is the size. It just gets the size of the linked list. And similarly, this checks if the linked list is empty. Those are both pretty self-explanatory. Okay, next interesting method is the peek method. The peek method returns the element that's at the front of the queue, but it will throw an error if your queue is empty, because you can't peek anything when your queue is empty. Similarly for poll, this will poll the element at the front of the queue, but unlike peek, will actually remove the element from the queue. So next, we scroll down a little bit. I have offer, which adds an element to the back of the queue. I guess I am allowing for null elements. So if you don't want null elements, just put an if statement and throw an error or something. So the poll removed from the front, and you can see offer adds to the back. So remove first and add last. And the last method in here is an iterator in case you want to be able to iterate through all of the elements in your queue. Very short and very simple implementation, just under 50 lines of code. You can create a queue. Although there are faster ways of creating queues, especially with arrays. The idea with arrays, especially static arrays, if you know the maximum amount of elements that will be in your queue at any given time, then you can create an array of that maximum size and have pointers to the front and the back positions in your queue, and add and remove elements based on the relative position of those pointers. If you ever get to a position where you're running off the edge of your array, then you can loop around to the front of the array and keep processing elements like that. This is a lot faster than having to maintain references to the next node, such as in a linked list. So I guess I'll say that's your homework, is to create a static array based queue. Today we're going to talk about everything to do with priority queues, from where they're used to how they're implemented, and towards the end we'll also have a look at some source code. Along with all the priority queue stuff, we're also going to talk about heaps, since both topics are closely related, although not the same. So the outline for the priority queue series is we're going to start with the basics, talking about what are priority queues and why they're useful. Then we'll move on to some common operations we do on priority queues, and also discuss how we can turn min priority queues into max priority queues, followed by some complexity analysis. Then we'll talk about common ways we implement priority queues. Most people think heaps are the only way we can implement a priority queue, or that priority queues somehow are heaps. I want to dispel that confusion. Next, we're going to go into some great detail about how to implement the priority queue using a binary heap. There we'll look at methods of sinking and swimming nodes up and down our heap. These terms are used to, again, shuffle around elements in a binary heap. As part of the implementation explanation, I also go over how to pull and add elements. So there's a lot to cover, so let's get started. Discussion and examples. This is going to be part 1 of 5 in the priority queue series. So what is a priority queue? A priority queue is an abstract data type that operates similar to a normal queue, except for the fact that every element has a certain priority. So elements with a higher priority come out of the priority queue first. As a side note, I would like to remark that priority queues only support elements that are comparable, meaning that the data we insert into the priority queue must be ordered in some way, either from least to greatest or greatest to least. This is so we can assign relative priorities between elements. Okay, let's go into an example. So suppose we have all these values that we inserted into our priority queue on the right, and that we impose an ordering on the numbers such that we want to order them from least to greatest. So the smaller numbers have a higher priority than the bigger ones. So they will be removed from the priority queue first. Suppose we have now a list of instructions. So what the pull operation means is remove the element that has the highest priority in our priority queue. So let's see how this works. So if I say pull, then I remove the element with the highest priority, which happened to be 1. Now I say add 2, so we add 2 to our priority queue, and poll. So next we poll the smallest elements in our priority queue, and that happened to be the 2 we just added. Next we add 4, poll the smallest, this is 3, add 5, also add 9, and then poll the rest. So as I pull the rest, I'm continuously grabbing the smallest element in the priority queue. So it turns out that as we added and pulled numbers, we got an ordered sequence. This is a coincidence, actually. As we add and pull numbers from the priority queue, we do not necessarily end up getting an ordered sequence. We are only guaranteed that the next number that is removed from the priority queue is the smallest number that was currently in the priority queue. So how does the priority queue know which is the next smallest number to remove? As humans, we could see the numbers visually inside the priority queue and look and know what one was the smallest the pull operation was going to return. But fundamentally, how does the machine know this? Does it resort all the elements inside the priority queue before each pull operation? No, in fact, that would be highly ineffective. Instead, it uses what is called a heap. So the next big question then is, what is a heap? Usually I make up my own definitions, but I really like this one from Wiki. A heap is a tree-based data structure that satisfies the heap invariant, also called the heap property. If A is a parent node of B, then A is ordered with respect to B for all nodes A and B in the heap. What this means is the value of the parent node is always greater than or equal to the value of the child node for all nodes, or the other way around, that the value of the parent node is less than or equal to the value of the child node for all nodes. This means we end up getting 2 types of heaps, max heaps and min heaps. So max heaps are the one where the parent node is always greater than its children, and the min heap is the opposite. So both of the following are actually binary heaps. Binary because every node has exactly 2 children, and the children you cannot see are null values I have not drawn in. So why are we interested in heaps? Well, heaps form the canonical underlying data structure for priority queues. So much so that priority queues are sometimes called heaps, although this isn't technically correct, since the priority queue again is an abstract data type, meaning it can be implemented with other data structures also. Okay, we're going to play a little game. I'm going to give you some structures, and you need to tell me whether it is a heap or not. So inspect the following structure and try to determine whether it's a heap or not. You can pause the video if you like, but I'm just going to give you a short moment here. No, we have a violation of the heap invariant in this tree, so it's not a heap. Is this structure a heap? Yes, it is a heap because it satisfies the heap invariant and it is a tree. So we often see heaps like these in what are called binomial heaps. Note that heaps aren't necessarily binary heaps, they can have any number of branches. On to our next one. So is this a valid heap? Yeah, it's a valid heap, because even though this one is strangely structured, we're free to move around the visual representation of the nodes as we please. So yeah, it's a valid heap. How about this one? No, this structure is actually not even a tree because it contains the cycles. All heaps must be trees. What about this one? Yeah, it's a heap. What about this one? Also a heap, because it satisfies the heap invariant that all nodes are less than or equal to or greater than or equal to its parent. How about this one? No, it's not a heap because it does not satisfy the heap invariant. However, if we do change the root to be 10, then we can satisfy the heap invariant via a min heap. Or rather, sorry, a max heap. So when and where is a priority queue and a heap used? Probably one of the most popular places we see priority queues is in Dijkstra's shortest path algorithm to fetch the next nodes we explore. Priority queues are really handy anytime you also need a behavior in which you need to dynamically fetch the next best or the next worst element. They're also used in Huffman encoding, which is often used for lossless data compression. Many best first search algorithms use priority queues in their implementation to continuously, again, grab the next most promising node in the graph as it's being traversed. And finally, we also see priority queues in Prim's minimum spanning tree algorithm on directed graphs. So it seems priority queues are really important, especially for graph theory algorithms, which is where we see them often. Okay, on to some complexity with priority queues implemented as a binary heap. So to begin with, there exists a method to construct a binary heap from an unordered array in linear time. We're not going to cover this algorithm, but it's pretty cool, and it forms the basis for the sorting algorithm heap sort. Next is pulling or removing an element from the root of the heap. This takes logarithmic time because you need to restore the heap invariant, which can take up to logarithmic time. So peeking or seeing the value at the top of our heap can take constant time, which is really nice. Adding an element to our heap takes logarithmic time, again because we possibly have to reshuffle the heap by bubbling up the value, as we will see in a later video. Then there are a few more operations we can do on priority queues. So removing an element which is not the root element. So the naive way of removing an element in a heap is to do a linear scan to find the item's position and then remove it. Well, the problem with this is it can be extremely slow in some situations, especially if you're removing a lot. But generally you don't do this and it's not a problem, which is why most implementations are just, lazy and do the linear scan solution. However, there does exist a way to reduce the removing time complexity, which I will go over later in a later video in great detail in this video series, so stay tuned for that. This method uses a hash table to reduce the removing time complexity to be logarithmic, which is super critical actually if you're removing as much as you are adding. Now the naive method to check containment within a heap, a binary heap, is linear. Again, you just scan through all of the elements, but with the help of a hash table, we can reduce this to be a constant time, which is super neat, especially if we use the hash table implementation for the removing speedup. We get that as a free bonus. The downside, however, to using the hash table implementation is that it does require an extra linear space factor, and it does add some constant overhead because you're accessing your table a lot during swaps. Today we're going to talk about turning min priority queues into max priority queues. This is part 2 of 5 in the priority queue series. So you may already be asking yourself, why is it important that I know how to convert a min priority queue into a max priority queue? Well, here's the problem. Often in the standard library of most programming languages, they will only provide you with either a max priority queue or a min priority queue. Usually it's a min priority queue, which sorts elements by the smallest element first, but sometimes we need the max priority queue depending on what we're programming. So how do we do this? How do we convert one type of priority queue into another type? Well, a hack we can use is to abuse the fact that all elements in a priority queue must implement some sort of comparable interface, which we can simply negate or invert to get the other type of heap. Let's look at some examples. Suppose for a moment that we have a priority queue consisting of elements that are on the right side of this screen, and that these are in a min priority queue. So if x and y are numbers in the priority queue, and x is less than or equal to y, then x will come out of the priority queue before y. The negation of this is x is greater than or equal to y. And so y then comes out before x, because all these elements are still in the priority queue. Wait a moment, you say. Isn't the negation of x is less than or equal to y just x greater than y, and not x is greater than or equal to y? Well, not for comparators. You see, if x is equal to y, whether or not the comparator is negated, x should still equal y. So now let's see what happens when we pull all these elements out of the priority queue with our negated comparator. So first we would get 13 because it's the greatest, and next comes 11, 7, 5, 3, and 2. An alternative method for numbers is to negate the number before you insert it and negate it again when it comes out. This is a hack specific to numbers, but it's pretty nice. So let's see how that works. So let's negate all the numbers inside our priority queue, and now we can see that definitely minus 13 is the smallest, so it should come out first. So minus 13 indeed comes out first, but now we have to negate it and we get 13. Everything is good so far. Next is minus 11, so really positive 11, and so on, minus 7, 7, and so on. Just so keep pulling and then renegate the value to get it out of the priority queue. It's a pretty neat hack. Okay, now let's look at another examples using strings. So suppose lex is a comparator for strings, which sorts strings in lexicographic order. This is the default for most programming languages. Then let's call nlex be the negation of lex. And also let's assign s1 and s2 to be some non-null strings. So below you can see that our comparator assigns minus 1 if s1 is less than s2 lexicographically, 0 if they're equal lexicographically, and plus 1 if s1 is greater than s2 lexicographically. And then nlex is just the negation of that. So just to break it down, lex sorts strings lexicographically, but we're interested in negating lex so that longer strings appear before shorter strings, and also that strings with letters at the end of the alphabet appear before those containing letters at the beginning of the alphabet. I think I said that right. This would in effect turn a min heap into a max heap. Let's look at a concrete example. So by adding all the numbers on the right to our priority queue with a lexicographic comparator, here's the ordering we should expect. First we get A because it's the shortest string that has characters appearing closest to the start of the alphabet. Then it comes out B, then F, Z, then X, then XR, and XX. So now let's do the same thing but with nlex. And we should hopefully obtain the opposite sequence in reverse order. And then we get XX, XR, X, F, Z, B, and A. So it did exactly what we intended it to do. Today we're going to talk about adding elements to a binary heap. This is part 3 of 5 in the priority queue series. We'll get to adding elements to our binary heap shortly, but first there's some important terminology and concepts leading to that, which we need to go over prior to add elements effectively to our priority queue. Okay, so a very popular way to implement a priority queue is to use some kind of heap. This is because heaps are the data structure which give us the best possible time complexity for the operations we need to perform with a priority queue. However, I want to make this clear. A priority queue is not a heap. A priority queue is an abstract data type that defines the behavior a priority queue should have. The heap just lets us actually implement that behavior. As an example, we could use an unordered list to achieve the same behavior we want for a priority queue, but this would not give us the best possible time complexity. So concerning heaps, there are many different types of heaps, including binary heaps, Fibonacci heaps, binomial heaps, pairing heaps, and so on and so on. But for simplicity, we're just going to use the binary heap. A binary heap is a binary tree that supports the heap invariant. In a binary tree, every node has exactly 2 children. So the following structure is a binary heap, which satisfies the heap property that every parent's value is greater than or equal to that of the child, that every node has exactly 2 children. Well, now you may be thinking, the bottom nodes, also known as leaves, don't have children. Well, actually, yes they do. Here they are. They're the null children in gray. But for simplicity, I won't draw those because they're annoying to draw. Okay. The next important bit of terminology we need to understand is the complete binary tree property. The complete binary tree property means that at every level, except possibly the last, is completely filled, and that all the nodes are as far left as possible in the binary tree. As you will see, when we insert nodes, we always insert them at the bottom row, as far left to meet this complete binary tree property. Maintaining the complete binary tree property is very, very important because it gives us an insertion point no matter what the heap looks like or what values are in it. The next node we insert will go into the hollow circle, and the next one will go to the right of it, and so on until eventually we fill up the row, at which point we need to start a new row. So the insertion point is very important. One last thing before we actually get into how to add values into our binary heap is we need to understand how to represent one of these binary heaps. And there is a canonical way of doing this, which is to use an array, actually. So using an array is very convenient, actually, because when we're maintaining this complete tree property, the insertion position is just the last position in our array. However, this isn't the only way we can represent a heap. We can also represent a heap using objects and pointers and recursively add and remove nodes as needed, but the array construction is very elegant and also very, very fast. So on the left is the index tree, just to help you visualize the position of each node in the array, and on the right is the actual tree. Remark that as you read elements in the array from left to right, it's as though you're pacing through the heap one layer at a time. So if we're at node 9, which is index 0, we're at the top. If we're at node 8, we're at position 1. Then as I keep moving along, you can see that we're just pacing through the array going from left to right. So it's very convenient that way. And also, another interesting property of storing a binary heap in an array is that you can easily access all the children and parent nodes. So suppose I is the index of a parent node. Then the left child is going to be at index 2 times I plus 1. And the right child of that node is going to be at 2I plus 2. This is 0 base. If it's 1 base, then you would just subtract 1. So suppose we have a node 7, which is highlighted in purple. Well, its index is 2, so by our formula, the left child of 7 should be located at 2 times 2 plus 1, or 5. And if we look at index 5, we expect to get 1, and if we look at the right child, we should expect to get 2 times 2 plus 2, or 6. If we look in our array, this gives us the value of 2. So using this technique, we have all we need to manipulate the nodes in our array. In the source code I will be presenting in part 5 of this series, we'll see that I use this representation for simplicity. Alright, so now we want to know, how do I add nodes to a binary heap and maintain the heap invariant? Because if we add nodes to our binary tree and we don't maintain the heap property, well, the binary heap is useless. We'll do some examples. On the left, I have some instructions which tell us what values we need to insert into the heap. The first value is a 1, which we can see, which should actually appear at the root, since we're dealing with a min heap. But instead of inserting 1 at the root directly, what we do is we put 1 at the bottom left of the tree in the insertion position I was talking about, and perform what's called bubbling up, as my undergrad prof loved to say. This is sometimes called swimming or even sifting up. All really cool names for a really neat operation. So we insert 1 in the insertion position, but now we're in violation of the heap invariant, since 1 is less than 7, but 1 is found below 7. So what do? What we do is we swap 1 and 7, like so. But now we're still in violation of the heap property, since 1 is a child of 6, but 1 is less than 6. So what do? We swap them. But yet again, in violation of the heap property, so we swap, and now 1 is at the root, where it should be, and now the heap invariant is satisfied, and we can stop swimming or bubbling up or whatever you want to call it. So the next one is 13, so as usual, begin by putting it in the insertion position, and now we need to satisfy the heap invariant, so bubble up 13. Notice that we're no longer in violation of the heap property, since 14 is less than 13 and 13 is less than 12, so 13 is actually in its correct position. Sometimes we don't have to bubble up our elements that much. The next values we need to insert are 4, 0, and 10. Try seeing where these end up. Pause the video if you need. It's a good little exercise. But I will keep going for now. So 4 goes in the insertion spot left of all the nodes on its layer. And we bubble it up until we can't anymore. And we stop. The heap property is satisfied. Next is 0, my favorite number. Of course, I've arranged that 0 be at the top of the tree, as you will see. So right now we're in violation of the heap invariant, so let us bubble up. And like magic, 0 is at the top of the tree. Next is to insert 10. The next number is 10, so we put it at insertion position. And however, this does not violate the heap invariant, so we do nothing. Today we're going to be looking at how to remove elements from a binary heap. This is part 4 of 5 in the priority queue series. Make sure you watch the last video so you understand the underlying structure of the binary heap. So let's get started. In general, with heaps, we always want to remove the root value because it's the node of interest. It's the one with the highest priority because it's the smallest or the largest value. When we remove the root, we call it polling. A special thing about removing the root is that we don't need to search for its index, because in an array implementation, it has position or index 0. So when I say poll, in red we have the node we want to remove, and in purple is the one we're going to swap it with. So the node in purple is always going to be the one at the end of our array, which we also have its index. So we swap them, we get rid of the 1, and now, since 10 is at the top, well, we're not satisfying the heap invariant. So we need to make sure that the heap invariant is satisfied. So we need to do what's called bubbling down now instead of bubbling up. So what we do is we look at 10's children, 5 and 1, and we select the smallest, and we swap with the smallest. So 10 would go to 1. So make sure you default selecting the left node in case there was a tie. So as you can see, 10's children are 2 and 2. They're both equal, so we're going to select the left node to break the tie. And now we bubble down 10 again, and now the heap invariant is satisfied. Now we want to remove the value 12. So polling was removing the element at the root, but 12 is not at the root. However, we still want to be able to remove 12. So what we do is we have to search for 12 in our tree, even though we don't know its position yet. So we start at 1, and we do a linear scan through all our elements until we find 12. So 5 is not 12, 2 is not 12, and so on until find 12. And now we found 12, and now we know where its position is, so we can mark it as the node we want to remove, and also swap it with the purple node being the last node in our tree. Swap them, remove the 12, and now we're in violation of the heap invariant, so now we want to bubble up 3 until the heap invariant is satisfied. And now we've satisfied the heap invariant, so we can stop. Now we want to remove 3, same thing as last time, search for 3 in the tree. 3 wasn't far, it was just 2 nodes away. So now, to remove an element, again, swap it with the last node in the tree, drop it. But now the question is, do we bubble up or bubble down the value? Because you don't really know what the value of the node in the last position is when you're swapping it in. So do we bubble up or bubble down? Well, we already satisfied the heap invariant from above, so we need to bubble down 15. So 5 was smaller, so we swapped it with 5. Now 8 is smaller, so we swap it with 8. And again, the heap invariant is satisfied. Now we want to poll, so mark the root node red, swap it, remove the 1, and now we would want to bubble down, and the heap invariant is satisfied. Now we want to remove 6, so search for 6 in our tree. Okay, we have found 6, and do the swap, remove 6. Now do we bubble up or bubble down? The answer is neither, the heap invariant is already satisfied, so we don't even need to touch our node. We got lucky. Okay, so from all this polling and removing, we can conclude the following. That polling takes logarithmic time, since we're removing the root and we already know where to find it, and also that removing a random node can take up to linear time, since we have to actually find the index of that node we want to remove before removing it. However, if you're as dissatisfied with this linear removal as I am, you would figure out that there has to be a better way. And indeed there is, and I'm about to show you a hack to improve this complexity to be logarithmic in the general case. So stay tuned. Okay, so now we're going to look at how to remove nodes from a heap with the improved time complexity. To do this, we'll need to make use of a hash table, a data structure I have not yet covered, so buckle up, things are about to get a little wild. I promise I'll cover the hash table thoroughly in a later video, but right now it's going to look like magic. Back to the central issue, we have a bunch of nodes scattered across our heap at some positions, and instead of doing a linear scan to find out where the node we want to remove is, we just want to be able to do a lookup and figure that out. The way we're going to do this is that every node is going to be mapped to the indexes found at. So when we want to remove a particular node, we just look up its index instead of doing a linear scan. Sounds good, right? That sounds great, except for one caveat or two. What about if the heap has multiple nodes with the same value? What problems would that cause? Well, just a few, but nothing we can't handle. To begin with, let's talk about how we can deal with the multiple value problem. Instead of mapping one value to one position, we will map one value to multiple positions. And we can do this by maintaining a set or a tree set of indices for which a particular node value or key, if you want, maps to. So we're going to example. Okay, so observe the blue heap. Remark that it has repeated values. Namely, we can see that the 2 is there 3 times, 7 is there twice, 11 and 13 once. Below I have drawn the index tree, a tree which can help us determine the index position of a node in the tree. 11, for example, is at index 3, 13 at index 5, and the first 2 at index 0. On the left is the hash table with the key value pairs. Notice that 2 is found in 3 positions, 0, 2, and 6, while 7 is found in 2 positions, 1 and 4, and so on. So this is how we're going to keep track of the positions of the values in the tree. If nodes start moving in the tree, we also need to keep track of that. For example, if a bubble up or a bubble down occurs, we need to track all of those movements and where the swaps go to so we can update the index position in our map. If we swap 13 and the last 7, for example, the following should happen. So we look at where 7 and 13 are in our table, and then I've mapped those respective positions as red for the 7 and yellow for the 13. And this is what happens when we do a swap. We do a swap in the tree, but also in the table. And that's it. Okay, so this all sounds great. We keep track of repeated values by maintaining a set of indices a particular node with a particular value is found at. But now let's ask a further question. If we want to remove a repeated node in our heap, which node do we remove, and does it matter? Because if we look in our heap right here, there's 3 possible 2 values we could remove. Does it matter which one we remove? The answer is no, it does not matter. As long as, in the end, we satisfy the heap invariant. That's the most important thing. So let's look at an example, not just of removing, but also of adding and pulling elements with this new scheme I just proposed. It's not that hard, trust me. So first one, we want to insert 3. So we need to place 3 at the bottom of the heap in the insertion position. We also need to track where the new node is, so we add 3 to our table, along with its position, which happens to be at index 7. Look at the index tree in gray to confirm this. Now that 3 has been inserted, we need to make sure the heap invariant is satisfied. Currently it is not. So what we do is we bubble up 3. The parent of 3 is 11, which is greater than 3, so we need to swap those two nodes. I've highlighted the 7 in the index tree because it maps to 3 in the heap and 3 in the index tree because it maps to the value 11. Now swap those both in the tree and in the table. Awesome. Now the heap variant is still not satisfied, so do a similar thing for the node above. We grab the parent and do a swap in the tree and the table. And now the heap invariant is satisfied. So 3 has been inserted successfully. The next instruction is to remove 2 from the heap. So which 2 should we remove? Well, as I said, it doesn't matter as long as we satisfy the heap invariant in the end. If we remove the last 2, we can immediately satisfy the heap invariant with one swap. But for learning purposes, I'll simply remove the first one found in our set, which happens to be located at index 0. So we want to remove the 2 at position 0. So how do we remove a node again? So we did a lookup, so we didn't have to do that linear scan, which was nice. And now we swap it with the last node, which happens to be 11. We remove the last node. Now we need to satisfy the heap invariant. So we need to bubble down 11. So we look at 11's children, which happens to be 3 and 2. 2 is smaller, so it's the one we're going to swap with. So swap it in the table and in the tree. Now we are still not in satisfaction of the heap invariant, so look at 11's children being 13 and 2. 2 is smaller, so swap it with 2. And that's it. We're done. The last instruction says to pull, so get the value at the root, which is 2, and swap it with 11. Get rid of the 2, and bubble down 11. So as you can see, we're constantly updating our table, but still doing the same operations. This is part 5 of 5 in the priority queue series, and we're going to have a look at some source code for the priority queue today. So if you want the source code, here's a GitHub link with all the data structures in the series. The priority queue is one of them. Also make sure you've watched parts 1 to 4 so you can actually understand what's going on. Alright, let's dive into the code. Alright, here we are inside the source code. So notice that inside my priority queue, the types of elements I'm allowing inside my priority queue have to be comparable elements, as we talked about. So if they implement the comparable interface, then we are going to allow them inside our queue. So this is anything like strings, integers, anything with a comparable interface. So let's have a look at some of the instance variables. So I have the heap size. So this is the number of elements currently inside the heap. But then I also have another instance variable, which is the heap capacity. So this is going to be the size of the list that we have for our elements, which may be larger than the heap size is. And this is the actual heap, and we're going to be maintaining it as a dynamic list of elements using Java's list. Next, for our log of n removals, I'm also going to keep track of this map. And it's going to map an element to a tree set of integers. So these are going to be all the positions inside our heap, which we can find this element t. Alright. Next, I've got a few different constructors for our priority queue. We can just create a priority queue, and by default, I'm creating an initially empty priority queue with a capacity of 1. But I also allow you to create a priority queue with a defined initial capacity, which actually is more useful, because then we don't have to keep expanding our dynamic list every time. So I would recommend this. But also, even better, is if you know all the elements that are going to be inside your heap, you can actually construct the priority queue in linear time using an operation called heapify, which I didn't talk about in the slides, but can be very, very useful. So this just has all the usual setup stuff. Here I'm adding all the elements to the map, but also to the heap, and then here's the heapify process. So we start at about halfway through the heap size, and then we start decreasing, and then we sync all the elements. And you're like, wait a second, isn't this sync a logarithmic removal? Well, yes it is in the general case, but not if we're doing it in this fashion. I put a link to this paper up here just because the heapify operation isn't quite intuitive why it has this linear complexity. And if you look at the analysis in the paper, you'll end up seeing that the complexity boils down to a convergent series, and that's why we get a constant and we can say it's linear time. But in general, this isn't what you might be tempted to do if you're giving a collection of elements. You would initialize the heap, and then you would just use our add method to add the elements one at a time. And this will give you an n-log n bound. But definitely use the heapify whenever possible. Okay, now some pretty simple methods. We have isEmpty, just returns true or false if the heap is empty or not. Then clear. So when we clear the heap, we remove all the elements inside our heap array, but also inside our map. So that's why I call map.clear. Size returns a size. It's pretty simple. Peek, the first really useful method, just looks at the top of our priority queue, and if it's empty, returns null. Otherwise, we do a lookup at the first index inside our heap and return it because it's the root node. Poll, similar to peek, except that we're going to remove the very first element, and we're also going to return it because we want that information. Next, contains. So because we have a map with all our elements, we can do a map lookup to see if our elements inside the heap. And this reduces our complexity from linear, in which case we have to do a linear scan through all elements to check containment, to constant time, which is remarkable. But in the general case, people don't usually maintain this map. I just wanted to do it just to show you guys that it is possible. Although the map does add a lot of constant overhead you may or may not want. I personally find that the overhead is quite a lot, and I usually don't really remove things very frequently from maps, so it might not be entirely worth it. But it's up to you. If you're doing as many additions as you are removals, then definitely worth it. Alright, now let's have a look at the add method. So this method adds an element to the priority queue, and that element cannot be null. So what we do is first we check if our heap size is less than capacity. Otherwise, we have to expand our capacity of the heap. Next, we make sure we add it to the map so we keep track of it, and then we swim it up. Remember that we have to swim a node up because we add it to the very end of our list, and so we have to adjust where it goes inside our heap by swimming upwards. This next method, called less, is a helper method which helps me check if node I is less than or equal to node j, and this uses the fact that both elements, node 1 and node 2, are comparable, so we can invoke the compare to method. If we go back up, that comes from this interface, the comparable interface, which we needed. So let's scroll back down. Alright. So it returns true if I is less than or equal to j. Awesome. So next, this is the bottom-up node swim. So we are going to try to swim node k. So first we grab the parent of node k, and we can do that by solving for the parent. So remember that I'm working in, I'm starting at 0. Some people like to start their heaps indexed at 1. I like everything 0 based. So I get the parent, which is at this position, k minus 1 divided by 2, because we're going upwards. And while k is still greater than 0, so we're not at the root, and we are less than our parent, then we want to swim upwards. So we're going to swap the nodes, parent and k, and then k is going to become the new parent. And then we have to get the parent of k once more. And then we keep doing this, going up our heap and swapping nodes. So that's how you do the swim. So the sync is similar, but a little different. So this is a top-down node sync. And here we want to sync node k. And what we do is I grab the left node, but I also grab the right node. Remember, we're working 0 based, so +1, +2 instead of +0 and +1. And then I need to figure out which is less. Either it's going to be the left one or the right one. And I assume to start with that the left one is going to be smaller than the right one. And here I correct that hypothesis in case it was false. So I check that the right node is within the size of the heap, and if the right node is less than the left node, then the smallest one is going to be the right node. And our stopping condition is that we are outside the bounds of the tree, or we can't sync any more. And we kind of do a similar thing. We swap, and then k is the next smallest, kind of like we did in the last method also. So the swap method, I made an explicit method to swap because I also have to swap things inside the map and then set the values also. And this is really what adds a lot of the overhead for the map, is the fact that every time we call the swap method, we also have to swap things inside the map, which can be a lot of overhead, really. Technically, maps are constant lookup times, but the fact that you're doing all this internal hashing and collisions and whatnot, it can get costly. So remove. So if the element is null, return false, so we know we don't have any null elements inside our heap. So this is how you would do a linear removal in linear time. I commented out in case you want to revert back and remove the map and whatnot. Is you would scan through all the elements, and once you find the element you were looking for, just remove it at that index and return true. Otherwise, we're going to use our map. So get the index index of wherever one of the elements are. And if it exists, then remove it at that index. Okay, now let's have a look at the remove at method. So this is what I covered in the last video. So if our heap is empty, well, can't really remove anything. Otherwise, we're going to swap the index of what we want to remove with the last element, which is going to be at heap size. And then we're going to kill off that node and also remove it from our map. So if it so happened that I was equal to the heap size, meaning we just removed the very last element in our heap, just return the removed data. Otherwise, when we did the swap, we have to either sync that node up or down. And I'm kind of too lazy to check whether I need to sync or swim, so I just try both. So first I try syncing, and then if nothing happened, then I try swimming downwards. And in either case, return the removed data. Perfect. So this just readjusts where the swapped node position goes, either bubble up or bubble down. This method is just a method I use in my testing framework to make sure everything is good. So it checks essentially the integrity of the minimum heap. So initially you call this method with k equals 0, and that starts at the root. And it's going to recursively go down the tree and check, are we maintaining the heap invariant property, which we need. So our base case is going to be that k is outside the heap size. And if so, we're just going to return true. Otherwise, get our children, left and right. And now we're going to make sure that k is less than both our children. And if that's not the case, return false. And if we ever return false, because we have an AND statement when we're recursing right here, that gets propagated throughout the recursion, and this whole method will return false. Otherwise, if everything returns true and hits the base case, then we know for sure it's in a minimum heap. Okay, these last few methods are just map helper methods, so things to add things into the map, how to remove elements from the map, and so on. And what I'm doing here is I'm using a tree set to add and remove elements, because I know the tree set implementation in Java is a balanced binary search tree, so all operations on tree sets are logarithmic, which is really nice. So you guys can have a look at those in more detail. It just gets values, removes values, and lastly, do a map swap. So yeah, it just swaps values in the heap, or in the map rather. So you guys can have a look at those in more detail. But I pretty much covered everything about the priority queue. Alright, time to talk about the union find, also sometimes called the disjoint set. This is my favorite data structure. So let's get started. So an outline of things we'll be covering about the union find. First, I'll be going over a motivating example with magnets, just to illustrate how useful the union find can be. Then we'll go over a classic example of an algorithm which uses the union find, specifically Kruskal's minimum spanning tree algorithm, which is very elegant, and you'll see why it needs the union find to get the complexity it has. Then we're going to go into some detail concerning the find and the union operations, the two core operations the union find uses. And finally, we'll have a look at path compression, what gives us the really nice amortized constant time the union find provides. Okay, let's dive into some discussion examples concerning the union find. So what is a union find? So the union find is a data structure that tracks elements which are split into one or more disjoint sets. And the union find has two primary operations, find and union. What find does is, given an element, the union find will tell you what group that element belongs to. And union merges two groups together. So if we have this example with magnets, suppose all these gray rectangles you see on the screen are magnets. And also suppose that the magnets have a very high attraction to each other, meaning they want to merge together to form some sort of configuration. So if I label all the magnets and give them numbers, and we start merging the magnets with the highest attraction, first we're going to merge 6 and 8 together since they're the closest. So in our union find, we would say union 6 and 8. And when we do a lookup to find out which groups 6 and 8 belong to, they would belong to the blue group. Now perhaps 2, 3, and 4 are highly attracted to each other, so they would form a group. So they would form the yellow group. And perhaps 10, 13, and 14 would also form a group. And this keeps on going, and we unify magnets into groups. And perhaps we merge some magnets onto already existing groups, so we unify a gray magnet, which is just a magnet in its own group, to an already existing group. But also we can unify groups of magnets which are different colors. And then we assign it an arbitrary color, so blue, so suddenly everything in the yellow group went into the blue group. And now when we would do a lookup in our union find to determine which group, say 2, 3, or 4 are, now it would say, you're in the blue group. And the union find does all this merging and finding in a very efficient manner, which is why it's so handy to have around. I'm not explaining currently how that works, we'll get into that in a later video. This is just a motivating example. So where are other places that the union find is used? Well, we see the union find again in Kruskal's minimum spanning tree algorithm. In another problem called grid percolation, where there's a bunch of dots on a grid, and we're trying to see if there's a path from the bottom of the grid to the top of the grid, or vice versa. Then the union find lets us do that efficiently by merging together paths. Also, similar kind of problem in network connectivity are two vertices in a graph connected to each other through a series of edges. And also, perhaps in some more advanced examples like the least common ancestor in a tree, and also in image processing. So what kind of complexity can we attribute to the union find? The complexity is excellent. So its construction is linear time, which isn't actually bad at all. Then the union find, get component, and check if connected operations all happened in what's called amortized constant time. So almost constant time, although not quite constant time. And finally, count components. Well, we can determine how many components, or in our magnet examples, how many different groups of magnets we have, and we can do that in constant time, which is really, really great. Okay, let's talk about a really neat application of the union find, which is Kruskal's minimum spanning tree algorithm. So you might be asking yourself, what is a minimum spanning tree? So if we're given some graph with some vertices and some edges, the minimum spanning tree is a subset of the edges which connects to all the vertices and does so at a minimal cost. So if this is our graph, with some edges and some vertices, then a possible minimum spanning tree is the following and has edge weight 14, well, total edge weight 14. Note that the minimum spanning tree is not necessarily unique, so if there is another minimum spanning tree, it will also have a total weight of 14. So how does it work? So we can break it up into 3 steps essentially. So the first step is easy. Just take all our edges and sort them by ascending edge weight. Next thing we want to do is we want to walk through the sorted edges and compare the 2 nodes that the edge belongs to. And if the nodes already belong to the same group, then we want to ignore it because it'll create a cycle in our minimum spanning tree, which we don't want. Otherwise, we want to unify the 2 groups those nodes belong to and keep going. And we keep doing this process until either we run out of edges or all the vertices have been unified into one big group. And you'll soon see what I mean by a group, which is when our union find data structure is going to come into play. So if this is our graph, then to run Kruskall's algorithm on it, first let's scale the edges and sort them. So on the left side, you see I have all the edges and their edge weights sorted in ascending order. So next we're going to start processing the edges one at a time, starting with the top, so I to j. So I've parted the edge I to j in orange, and you can see that it connects nodes I and j. I and j currently don't belong to any group, so I'm going to unify them together into group orange. Next is edge A to E. So A to E don't belong to any group, so I'm going to unify them together into group purple. Next is C to I. So I belongs to group orange, but C doesn't have a group yet, so C can go into group orange. Alright, E to F. F doesn't belong to a group, so F can go to group purple. Next, H and G. Neither H nor G belong to a group, so I'm going to say you guys belong to the red group. Next, we have D to B. They also don't belong to a group, so give them their own group. Let's say group green. Alright, and now I believe this is when things start to get interesting. Now we're trying to connect C to J. But notice that C and J already both belong to group orange, so we don't want to include that edge because it's going to create a cycle, so ignore it. And to check that they belong to the same group, we would use the find operation in our union find to check what group they belong to. So this is when the union find really comes into play. Next is edge D to E. So note that E belongs to group purple and D belongs to group green. So now we want to merge them together because they don't belong to the same group. So either the purple group is going to become the green group or the green group is going to become the purple group. It doesn't really matter. So now we would merge them, and this is when the union operation in our union find becomes useful. It allows us to merge groups of colors together very efficiently, and that's the important note. Next edge would be D to H. H belongs to group red, and D to purple, so merge the groups together. Let's say they both become group purple. Next up, we want to add edge A to D, but A to D already belong to the same group, so that would create a cycle. So we don't want to include that edge. So skip it. Next, we want to include edge B to C. B to C belong to different groups, so merge the 2 groups into one larger group. So we have found the minimum spanning tree using Kruskall's minimum spanning tree algorithm. Pretty neat, right? So the underlying data structure which allows us to do this is the union find. It allows us to merge groups of colors together efficiently, but also to find out which groups nodes belong to, so that we don't create a cycle. So that's Crusoe's algorithm. It's super simple, given that you know how the union find works. So I'm going to go into some detail in the next video explaining how the find and the union operations work internally and how we can actually implement it in some useful way. Okay, so now we're going to talk about the union and find operations we can do on the union find, or the disjoint set. This is the video where I demystify how those actually work internally. So to create our union find, the first thing we're going to do is we're going to construct a bijection, or simply a mapping between our objects and the integers in the range 0 inclusive to n non-inclusive, assuming we have n elements. So this step in general is actually not necessary, but it's going to allow us to create an array-based union find, which is very efficient and also very easy to work with. So if we have some random objects and we want to assign a mapping to them, then we can do so arbitrarily, as long as each element maps to exactly one number. So that is my random bijection, and we want to store these mappings perhaps in a hash table so we can do a lookup on them and determine what everything is mapped to. Next, we're going to construct an array, and each index is going to have an associated object, and this is possible through our mapping. So for instance, in the last slide, A was mapped to 5, so slot 5, or index 5, is going to be A's slot. So what you see in this picture is at the top is that array we just created, which contains our mapping. And in the center is just a visual representation of what's going on. The value in the array for each position is currently the index which it is at. This is because originally every node is a root node, meaning it maps to itself. But as we perform the instructions on the left of unifying groups together, or objects together into groups, we're going to find that we're going to change the values in our array to map to other letters. And specifically, the way we're going to do it is for some index I in our array, index i's parent is going to be whatever index is at position I. So, for instance, if we want to unify C and K, we look at C and K, and we discover that C has a root node of 4, and K has a root node of 9. So either C is going to become K's parent, or K is going to become C's parent. And I chose that K's parent is going to be C. So now at index 9, which is K's position, I'm going to put a 4, because I know that C is a 4. So next, F and E, we're going to do a similar type of thing, and I'm going to say that F's parent is going to be E. So at F's position, which is 1, I'm going to put a 0, because E is 0. Similar thing for A and J. But here's where things get a bit more interesting. So now we want to unify A and B. So if I look, A has a 6 in its cell, but 6 is J. So I know that A's root node for group green is J, and B is a single node because it's a self loop. And in general, I'm going to merge smaller components into the larger ones. So now B is going to point to J because the green group's root node was J. So now we want to merge C and D. So I find the root node of D, which is D, and find the root node of C, which is C, and I'm going to merge the smaller component, D, into the larger component, which is the orange group. So now D is going to be part of the orange group. Now I want to merge D and I, so a similar thing happens, and I now points to C. Now I want to merge L and F. So F's parent is E, so I'm going to merge L and to be into the red group. Now I want to merge C and A. So this is an interesting example. So I find C's root node, which happens to be C, and I find A's root node, which is J. So now component orange has 4 elements, but component green only has 3. So I'm going to merge the green component into the orange component. So now J is going to point to C. So I want to unify A and B. So if I go up and follow the parent nodes until I reach a root node, A's parent is J, J's parent is C. So I know that A belongs to the orange group, and if I do a similar thing with B, I also discover that B's parent is also C, which is the orange group. So I don't need to unify them, they're already unified together. So H and G, they currently don't have a group, so I'm going to arbitrarily merge them into a new group, which is going to be the blue group. So H and F. So if I look, H's parent is G, and F's parent is E. The red component is larger, so I'm going to merge the blue group into it. And now, since G was the root node, I make it point to E, which was also the root node. Now I want to merge H and B. So H's root node is E, if we follow up the chain from H to G to E, and B's root node is C, because we go from B to J to C. So now, since the orange component is larger than the red component, I'm going to point the root of the red component to the root of the orange component, so E now points to C. Okay, and note that in this example, I'm not using a technique called path compression. This is something we're going to look at in the next video, which is an optimization on the union find. To summarize, if we want to find out which component a particular element maps to, what we have to do is find the root of that component by following all the parent nodes until we reach a self loop, or a node whose parent is itself, and that will uniquely determine which component that element belongs to. And to unify two components together, what we do is we find the root nodes of each component, and then if the root nodes are different, because if they're the same, and then they belong to the same component already, so if they're different, make one of the root nodes point to the become the parent of the other root node. So just some remarks about this union find data structure. So in general, we don't really ununion elements, just because this would be inefficient, as we'd have to update all the children which point to that node, and we don't have access to those. But we could probably, in theory, keep track of that. I just don't see any application currently, but there might be. Also, remark that the number of components in our union find is going to be equal to the number of root nodes remaining, because each root node is responsible for a component. And also remark that the number of root nodes never increases, it always decreases, because all we do is unify components, so components only get bigger and bigger and bigger. So now I want to talk about the complexity of the union find. So I said in the first video that the union find has an amortized time complexity. However, the implementation I just showed you does not have an amortized time complexity. Not yet. Not without the path compression, which is something we're going to look at in the next video, which is what makes the union find an absolute beast of a data structure. You must watch the next video. But just as an example, if we need to check if H and B belong to the same group or a different group, it's going to take 5 hops in the worst case, and, well, potentially much more. So H, we find the root node, which is C, and then we go from B, and then find the root node, which is also C. So this takes quite a few hops. Let's talk about path compression. Now, this operation is really what makes the union find one of the most remarkable data structures, because it's how the union find gets to boast in its efficiency. So let's dive right in. But before we get started, it's critical that you watch the last video so that you understand how the find and the union operation work. Otherwise, you won't understand what's going on and what's up with path compression and how we're going to get that really nice amortized constant time. Alright, suppose we have this hypothetical union find. I say hypothetical because with path compression, I'm almost certain it's impossible to achieve a data structure or a structure that looks like this. Nonetheless, it's a good example. So now suppose we want to unify nodes E and L, or just unify groups orange and blue, but we have access to E and L, and that's what we're calling the unify operation on. Well, we would have 2 pointers that start on E and L, and what we would want to do is find the root node of E and find the root node of L, and then get one of them to point to the other. But with path compression, we do that, but we're also going to do something else. So let's start by finding the parent node of E. So E's parent is D, and then D's is C, C to B, and B to A, and then A to F. So we found the root node of E, but with path compression, here's what we're going to do. Now that we have a reference to the root node, we're going to make E point to the root node. And similarly, D is going to point to the root node, and C, and B, and A. So now everything along the path got compressed and now points to that root node. And in doing so, every time we do a lookup on either A, B, C, D, or E in constant time, we will be able to find out what the parent or the root node is for that component, because we immediately point to it. We don't have to traverse a sequence of other nodes. And we can do this because in a union find, we're always unifying things together and making them more and more compressed. We're never ununifying things, if you will. So if we do the same thing for L, we find L's parent. So we traverse up all the parents until we find the root. And then we compress the path. So J points to G, I points to G, H points to G. And so we compress that path, but we also have found the parents now. So make one point to the other, and we've unified both groups. So now the group that was once with E and once with L have now been merged into one single group. But the only difference is we've compressed along the way as we've done this, and now it's so much more efficient. And now let's have a look at another example, and this one I want to compare and contrast the regular union find operations we were doing in the last video to the path compression version we now know. So if I run all those union instructions, this is what would happen. So I'd start by getting all these pairs of components, and then now I'm executing the instructions on the right. And this is the final state of our union find. And note that if I'm trying to determine what groups, say, A and J are in, then I have to traverse a whole bunch of different nodes. So J goes to I goes to H goes to E. But now if I include path compression, let's see what happens. So I still get all those components, but now as I execute the instruction on the right hand side, this is what happens. So I get the green group, but then because of path compression, that J merged into the H, so already that path is a little shorter. And then I keep executing more instructions, but as I'm doing it, the path gets compressed dynamically. So I'm getting more and more compression, and even up to the very end. So on the last example, we hadn't even finished all the instructions and we have reached the final state. But with path compression, as long as there's something to compress along our path, we get to compress the path along the way, pointing it to the root. So right now we only have one root, being E, and almost everything in constant time points to E. So we do a lookup on any of our nodes, and we know that the root is E, so we know it belongs to that component. And this structure becomes very stable eventually because of this path compression. This is why the union find with path compression is so efficient. Let's have a look at some of the union find source code. So here's a link to the source code. You can find it on my GitHub repository at github.com/WilliamFiset/data structures. I also have a bunch of other data structures from past videos. And before we dive into the code, make sure you watch the other videos pertaining to the union find, as I will be making some references to them. Okay, let's dig in. Here we are inside the code, and I have a class called UnionFind, and it's got a few instance variables, so let's go over them. The first is size, it's just how many elements we have in our UnionFind. Then I have these two arrays, one called ID and one called size. So the more interesting one is ID, and ID at I is that array I talked about, which at index I points to the parent node of I. And if ID at I is equal to I, then we know that I is a root node. So we're essentially keeping track of all of these tree-like structures right inside an array, which is practical. And also, because we create a bijection between our elements and some numbers, this is how we're able to access them through this ID array. And just for convenience, I track the number of components. That's sometimes some useful information you might want. So if you create a union find, well, you need to know how many elements are going to be inside your union find. And I make sure that we have a positive number of elements, otherwise I throw an exception. Then I go ahead and initialize some instance variables, and I initialize ID to equal I. So initially everyone is a root node, and every component has a size of 1. So find is pretty simple. It's given a node, it finds which component it belongs to and also does path compression along the way. So if we're at P and we want to find the root node of P, what we're going to do is we're going to find the root node using this one while loop. So we initialize a new variable called root to p, and then we loop until the root is not equal to id at root. So aka this is a root node or a self loop that we found, and so we can stop, and the root is stored in, well, the variable called root. And then what we do is we do the path compression. This is what I talked about in the last video. So starting back at p, we assign everything from id at p to equal the root. And this is what compresses the path and gives us that nice amortized time complexity. You can also do this recursively, but I don't like having the overhead, and doing things iteratively can be slightly faster. Okay, so now we have these simple methods we can call. So if P and Q are inside the same component, this will return true because the root at P and the root at Q will be equal. Otherwise, this will return false. And just calling find will do path compression. So even if we're just checking if two components are connected, and it calls the find method, then we're compressing the path. Same thing here. If we decide to find the component size relative to some index p, then when we index into the size and call find, we'll find the root, but at the same time we'll also do path compression, which is nice. And I would just like to note that the root nodes are the ones who will always contain the size, because they're the ones that are found, well, if you want to think about it, like at the end of the chain. Size just returns the number of components in our unified disjoint set. Components, number of components, that's pretty self-explanatory. And the unify method is the last interesting method. So this is the one that unifies two components together. So first what we do is we find what the root node for P is and what the root node for Q is. And if the root nodes are equal, then they're already in the same group and we don't do anything. Otherwise, by convention, I just merge the smaller group into the larger group. Although, I know some people like to keep the theoretical largest path in a component and then merge according to that. That may be slightly more efficient, but it's more work. So I just like to merge the smaller group into the larger group. And also, since the roots are different and we're merging, we know that the number of components or sets must have decreased by 1. So that's why at the bottom here, I say the number of components, subtract that by 1, because we know we're going to have 1 less component. So this whole time inside this class, I've been treating P and Q as integers and not as elements, like letters that we saw in the slides. And this is because of that bijection. I would do a lookup to find out what maps to the element P, and that should give me an integer, and what maps to the element Q, and then I could use those with this union find data structure I've created and turn everything into the realm of numbers instead of dealing with objects and having all this more complexity. It's much easier to have an array-based union find. You could also have a pointer-based union find with node objects, but this is really nice and it's a really clean implementation. Alright, I want to start talking about a very exciting topic, and that is trees. And you'll soon start to realize that there are tons and tons and tons of tree data structures. But today I want to focus on a very popular kind of tree, and that is binary trees. And with binary trees, we must talk about binary search trees as well. So today's tutorial is going to focus on binary trees and binary search trees, where they're used, and what they are. And in later tutorials, we're going to cover how to insert nodes into binary search trees, remove nodes, and also do some of the more popular tree traversals, which can apply to other general trees also, not just binary trees. Okay, so I'm going to give you guys a quick crash course on trees before we get started. So we say a tree is an undirected graph, which can satisfy either of the following definitions. There are actually multiple definitions, but these are the most popular ones. So a tree is an undirected graph which is connected and acyclic. Acyclic means there are no cycles. Another definition is we have n nodes, but we have n minus 1 edges. And lastly, for any two vertices, there's only one path between those two vertices. You can't have two different paths. That would imply that we don't have a tree because there's another route to get to another node. And so we'd have a cycle. Okay, in the context of trees, we can have something called a rooted tree, which is the topmost node of our tree. You can think of it that way. And if you're trying to root the tree and you don't have a root yet, it doesn't matter which node you pick to root the tree, because any node you pick can become the root node. Think of it as picking up the tree by that node and suddenly it's the new root. We have something called, or the concept of child and parent nodes. So a child node is a node that extends from another node. Think of it as going downwards, and a parent node is the inverse of this, so you're going like up towards the root. So we have an interesting question, and that is, what is the parent of the root node? The answer is that the root node has no parent, although sometimes it may be useful to say that the parent of the root node is itself. And we see this often when programming. For instance, a file system tree has this property. So if I open up the command line, I'm in some directory, so I can say pwd to get the current directory. So I'm somewhere in the file system tree, and if I want to go up to my parent, I can say cd // and now I'm up in another directory, or into the parent directory. And I can keep doing this and going up and up in the file system tree directory system. But if I go directly to the root node, which is /, and I see that I'm in the folder /, so the very top, at the root of the directory, and I say cd .. then if I check out where I am, I'm again at the root. So in this context, for a file system, the parent of the root is the root. Pretty cool. So just as an example, if we pick the node 0, it has two children, 3 and 2, and a parent 4. We also have the concept of something called a leaf node. This is a node which has no children, and these have been highlighted in orange. So they're just at the very bottom of your tree. Think of it that way. And there's also another term, which is a subtree. This is a tree entirely contained within another tree. And we usually use triangles to denote subtrees. And it's possible for a subtree to consist of only a single node. So that's fine. So if this is our tree with that circle node being the root, and we pick a particular subtree and look what's inside of it, then we get another tree, which contains nodes and more subtrees. Then we pick another subtree, we look what's inside of it, and then we get another tree. And eventually we're going to hit the bottom. So now we can pose the question, what is a binary tree? And this is simple. This is a tree in which every node has at most 2 children. So both those trees below are binary trees because they have at most 2 children. You can see that the tree on the right, 8, has 1 child, and that's fine because the criteria is at most 2. So now we're going to play a game. I'm going to give you some various structures, and you're going to have to guess whether it is a binary tree or not. So is this a binary tree? Yes, yes it is. Every node has at most 2 children. How about this one? No, you can see that 7 has 3 children, so it's not a binary tree. How about this one? Let you guys think about it a bit more. Yes, this is a binary tree. It may be a degenerate one, but it's still a binary tree. Alright, let's move on to binary search trees. So what is a binary search tree? Well, first of all, it's a binary tree, but furthermore, it also satisfies what's called the binary search tree invariant. And that is that the left subtree has smaller elements than the value of the current node, and the right subtree has larger elements than that of the current node. So below are a few binary search trees. We're going to play the same type of game, and I'm going to give you some trees, and you're going to have to guess whether they're binary search trees or not. So what about this structure? And this one, we could say it depends on whether you want to allow duplicate values inside your tree. It so happens that binary search tree operations allow for duplicate values. There's nothing wrong with that. But most of the time, we're only interested in having unique values inside our tree. So this particular tree depends on what your definition of a binary search tree is. How about this tree? Yes, this is a binary search tree. How about this tree? Notice I've only changed the elements within the tree. Yes, this is also a binary search tree. We're not limited to only having numbers within our binary search tree. We can place any type of data which is comparable and can be ordered. How about this tree? No, this is not a binary search tree. And the reason is the node 9 is in the wrong position. When we would be inserting 9, we would have to place it in the right subtree of 8 because 9 is larger than 8, so it belongs in its right subtree. How about this structure? This structure isn't even a tree actually, because it contains a cycle. And the requirement to be a binary search tree is that you must be a tree. And this last one, I'm going to give you a bit more time to look at this one, because it's not a regular type of structure you might think of as a binary search tree. And the answer is yes, this structure does satisfy the binary search tree invariant, that every right subtree contains larger elements. You'll see that that is true, and also every left subtree, it contains smaller elements. It doesn't look like a tree, but it satisfies our definitions of a tree and a binary search tree. Okay, so we've been talking about binary trees, binary search trees. Where are they used? Why are they useful? So in particular, binary search trees are used in many implementations of abstract data types for sets and maps and so on. And they're also used to implement balanced binary search trees, which we'll probably get to in a later video. And you see binary trees and binary heaps. We've already seen this in priority queues when we're making a binary heap. But we also see binary trees in things like syntax trees. So you're parsing an arithmetic expression, then you place it in an abstract syntax tree, and then you can simplify your expression. Compilers and calculators use this to evaluate expressions. So whatever you punch in your calculator gets parsed into a binary tree and evaluated. And lastly, I just threw in a treep, which is another type of probabilistic data structure. So now let's look at the complexity of these binary search trees, because they looked very interesting and also very useful. And indeed they are. So in the average case, when you're just given some random data, the time complexity is going to be logarithmic, which is really good. So if you're inserting nodes, deleting nodes, removing nodes, searching for a value in a tree, whatever, the average time complexity is going to be logarithmic. And these binary trees, or binary search trees, are very easy to implement. So this is really good. However, in the worst case, if your tree degenerates to being a line, then we can have some linear behavior going on, which is really bad. So there's some trade-offs if you want to use just a pure binary search tree, that it's going to be easy to implement, and on average it's going to have this logarithmic behavior, but in the worst case, you might be looking at some linear stuff, which is not so good. Okay, let's have a look at how to insert some elements into a binary search tree. So let's dive right in. So first, to add elements to our binary search tree, we need to make sure that the elements we're adding are actually comparable, meaning that we can order them in some way inside the tree. Meaning at every step, we know whether we need to place the element in the left subtree or the right subtree. And we're going to encounter essentially 4 cases. So when inserting an element, we want to compare the value to the value of the current node we're considering to do one of the following things. Either we're going to recurse down the left subtree because our element is smaller than the current element, or we're going to recurse down the right subtree because our element is greater than the current element, or it might be the case that the current element has the same value as the one we're considering. And so we need to handle duplicate values if we're deciding to add duplicate values to a tree or just ignoring that. And lastly, we have the case that we've hit a null node, in which case it's time to create a new node and insert it in our tree. Let's look at some animation now. So on the left, I have a bunch of insert instructions. So we have all these values we want to insert into our binary search tree. And currently, the search tree, or the binary search tree, is empty. So first we want to insert 7. So 7 becomes the root of the tree because it's the first node. Next, we want to insert 20. So 20 is greater than 7, so we insert it to the right. Next, we want to insert 5. So we always start at the root when we're inserting. That's an important point. So you start at the root, and then you move your way down the tree to figure out where you want to insert the node. So we start at the root, and then we're like, oh, 5 is less than 7, so we're going to insert it to the left. Now 15, start at the root, go to the right because 15 is greater than 7, then to the left because 15 is less than 20. Now 10. Now 4, so 4 is less than 7, move left. 4 is less than 5, move left, create the new node. Now we have 4 again, so let's see what happens here. So we start at 7, we move to the left, we move to the left. Now we've encountered a value that already exists in our tree. So as I said before, if your tree supports duplicate values, now's the time to add another node. And you would either pick by convention if you want it on the left or on the right. Otherwise, you would do nothing, and I'm going to choose to do nothing. I want to insert 33. So start at the root, go to the right because 33 is greater, go to the right again. Now insert 2. So 2 is smaller than everything in our tree, so it would go all the way to the left. Now try and see where 25 would go. So 25 is going to go to the right, then we're going to go to the right again because it's greater than 20, but we're going to go left now because it's less than 33. And finally 6, so once left, once right, and we've inserted everything into our binary search.